Hello, hello. It's not working this. Now it's working. Anista? Hello, everyone. Good morning. Welcome to the morning session in the focus meeting number 8. So the first speaker today is Lauren Job, who will give an invited talk on dynamos in non-convective zones. So please go ahead.
All right, thank you. So I have only this, so the pointer is also on this, or is anything else? All right, is it working? Yes, it seems. All right, so I can start maybe, yeah? So, I want to thank the organizers first for the invitation to talk about non-convective, or we can also say radiative zones of stars, whether they are convective or radiative. I'm going to give a little bit of an overview of what we know from now for the magnetic fields, and a little bit also about rotation in these radiative zones. And I'm going to talk a little bit about the work I've been doing with colleagues in Toulouse. So let's try this. Right? Big one, no, not this one. Big green, yeah. Not working, yes. All right, so, and the pointer is working indeed. Sorry. Pointer, no, what? I don't have any other device. Okay. Okay, it's fine. All right, so since I'm going to talk about the radiative zones of stars, I'm going first to show you this HR diagram where you see the shaded regions, where you have the blue region where the stars are fully convective. So this is the case for pre-main sequence stars or very low mass stars, also on the main sequence. Then the green shaded region is a region where you have a radiative core. So I'm going to be focusing in this talk on the radiative core of red giant stars, which are the stars which have evolved after the main sequence. They are post-main sequence stars, and they are really interesting, as already we saw yesterday with Savita Mathur talk. I'm also going to talk about some more massive stars. So we had a talk already yesterday about magnetism of massive stars. So I'm going to review again a little bit what has been told about this. So let's start first with the intermediate mass and massive stars. It takes a while to go from one to the other. Sorry about this. Yeah. So what we know about the magnetism of intermediate and massive stars is that we have something like 5 to 10% of these stars which show a very strong magnetism. It's strong magnetic fields, mostly dipolar or slightly inclined with the rotation axis. Something which is quite sorry. How do I go back? Yes. Something which is quite impressive with these stars is that if you look at the histogram of weak fields, AP-BP stars, so these are the ones which are strongly magnetic, then what you can see is that they all possess a strong magnetic field. It's all above something like 300 Gauss. And you see nothing below this value. So it's not an observational bias because it's easy to see fields which are also below 300 Gauss. It just seems that there is a minimum field in these AP-BP stars. And that's not completely obvious why we have such a minimum field. There is another population now of magnetic stars that are seen in this intermediate mass. Is the so-called Vega-like magnetism after the star for which it was first discovered through spectroperimetry. And what you see here is that this Vega-like magnetism, it's much more complex. It's not a dipole, it's a complex magnetic field. And the amplitude is the order of 1 Gauss or even sub-Gauss magnetism. That's why it's always been very difficult to see, of course. But now we have a couple of stars where we have this. actually something like 10 stars, where we see this magnetism when we also need to explain maybe the origin of this particular magnetism. Now for the red giants, so Savita, I'm glad Savita already presented this yesterday. We have, in fact, in these red giant stars, the first discovery of a magnetic field inside a star, in the very core, in the very radiative core of this red giant. This is amazing. We now have direct detection through asteroseismology of magnetic fields in these stars. So this is done by looking at the asymmetry in the in the multiplet, so I don't have a pointer. So the rotation is breaking is lifting the degeneracy with the various m's, as Savita showed yesterday. And this is going to be symmetric with respect the m equals +1, -1, or symmetric with respect to the m equals 0. But when you have magnetic fields, you are going to have asymmetries. So that you see at the bottom, on the bottom panel. And this has been seen in tens of stars now, of red giant stars. And from this, you can actually get the amplitude and a bit of knowledge of the topology also of the magnetic field in these stars. So we have strong, very strong fields in these stars, something like 100 of kilogauss, with various geometries, not necessarily dipolar ones. And there is now the question also of the origin of the magnetic field in these stars. Something which is great also with these red giants, then again, thanks to asteroseismology, is that we know a little bit about the rotation. We know a lot, in fact, about the rotation. So you know that these red giant stars, they finished burning hydrogen into helium in their core. They are post-main sequence stars, but now they are burning hydrogen in a shell around the core, or still in the radiative interior. And below this helium, this hydrogen burning shell, you'll have contraction of the core and expansion of the envelope above. And if you have contraction of the core, naturally, you expect to have a spin up of the rotation by just conservation of angular momentum, more or less. And in fact, the asteroseismology gives you the amplitude of the rotation of the radiative core, which is contracting. And in fact, what we see is that at the beginning, during the subgiant phase, number 1, there is evidence of solid body rotation. So in fact, despite contraction of the core and expansion of the envelope, there is no differential rotation being created. So there is probably a very efficient process of extracting angular momentum from the core because it's not pinning up, even so there is contraction. Then if you go to number 2, you evolve a little bit more on the giant branch. You have the more evolved subgiants, and there you see differential rotation, not as much as what you expect through hydrodynamical models, but you do have a differential rotation. And when you evolve even more on the red giant, the core rotation is not changing despite contraction again. So again, you need a very strong angular momentum extraction process to be in agreement with the observations. So this is a great great constraints for people doing numerical simulation and theory. And in particular, we need to understand these transport processes, which we know for the moment that the hydrodynamical processes are not enough to explain this. And so possibly the fact that there is magnetic field is going to help you. There are good candidates to transport angular momentum. Okay, so now theoretically, what can happen if you have rotation, differential rotation, and magnetic fields in a radiative zone? Okay, so we can ask this. So the basic thing you can think of is the omega effect. You have a poloidal magnetic field, you have differential rotation, which is going to shear it into a toroidal field, but then it's not going to do this for infinity. You need to have, then you're going to have a back reaction of your magnetic field on the differential rotation. And what it ends up with usually is what we call the Ferraro law of isorotation. Is the steady state is going to be that your isocontours of omega will be aligned with the magnetic field lines, with the poloidal magnetic field line. This is what you see at the top here, where you see the differential rotation in color being aligned with the poloidal field lines. Okay, so the magnetic tension may apply a strong forcing on the differential rotation. Then you can look at the magnetic equilibria. There's been a lot of work on all this, it's still going on. And in particular, you can be interested in how stable are these configurations, these equilibria. So you may have different kinds of instabilities. So what I'm going to focus on is the one which is called the magnetorotational instability. So it's an instability, in fact, of the shear, of the differential rotation, catalyzed by the presence of magnetic field. You need magnetic field to have the instability. But if the magnetic field is too strong, it's going to be stabilized. Another one is the Taylor instability. So this time it's an instability due to the current, so due to the magnetic field gradients themselves. And this doesn't like rotation. If rotation is too strong, the growth rate is decreasing a lot. Okay, so then you see that you can have distinction between the two instabilities when you compare the magnetic field amplitude with the rotation. If the magnetic field is strong enough compared to rotation, you're going to favor Taylor, and it's the opposite in the other case. All right, and one of the major ingredients in radiative zone is stable stratification. The fact that buoyancy is going to be a very strong restoring force. And that's bad news for instabilities or motions in general. Stable stratification is going to stabilize everything, okay? And MRI sometimes is considered to be more affected by stable stratification because the motions are going to be mostly parallel to gravity, so much constraint. Now, dynamos. So I haven't told you about dynamos yet. So you can have a dynamo action in radiative zones as well, despite you don't have convection, doesn't matter. You can still have differential rotation, which shears your poloidal field into a toroidal field. That's the basic thing you always also have in convection zone. But then you can have these non-axisymmetric instabilities, Taylor, MRI, buoyancy instabilities as well, which will produce fluctuations in the velocity and in the magnetic field. And as you see at the top, the U cross B, small u cross small b, is the correlations in the fluctuation, can again give you a mean axisymmetric poloidal field, which will be ready to be sheared again by the differential rotation, et cetera, and you start again. Okay, so theoretically it's possible. What do numerical simulations can tell us now? Do we manage to have this type of things happening, and does it help us with the observational constraints? Okay, so I'm going to present you a few MHD simulations done in 3D with the magic code, which is a public code, a pseudospectral. It's a spherical code where you're solving the 3D MHD simulations. And in particular, I'm going to give you two examples. So one example where you force differential rotation. So all the ingredients are there: differential rotation, magnetic fields, stable stratification, and you see what happens. Okay. So either you force differential rotation on very long time scales. This is what happens in red giants, for example. Contraction is going to force differential rotation, but on a time scale of contraction, which is something like billions of years, or millions or billions of years. And then you can have forcing on shorter time scales, and then I'm going to present you a few dynamo simulations that have been done in radiative zones. Okay, so now let's start with the forcing on long time scales, this contraction thing. So we try to have a ball of fluid where we have differential rotation forced by this contraction on long time scales, contraction time scales. So this is done by having a velocity forcing, a radial velocity forcing through this spherical shell. And then you have stable stratification, and you want to see what happens, okay? And you will put a magnetic field at some point. If you don't put any magnetic field, the natural differential rotation which is going to be produced is the shellular differential rotation that you see at the right, on the right, okay? Which builds up on non-time scale. This is a steady state, okay? But then if you have an initial magnetic field, you're going to put a large scale magnetic field. The relevant time scale now is the Alven time scale, which is super short compared to the contraction time scale. So the magnetic field is going to impose something on the flow. And in particular, you're going to see a magnetic tension at play and the iso rotation law, the Ferraro's law of iso rotation being applied in your system. So this is what you see at the top right. I hope you see delta omega over omega is the differential rotation which is created when you input a quadrupolar magnetic field here. So you see that you don't have a shellular differential rotation at all anymore because you now have your magnetic field imposing its law on the flow, okay? So magnetic tension is at play. And then what happens? This equilibrium becomes unstable. So this is what you see at the bottom left. Sorry about this. Ah, yes. Ah, no. Okay, sorry, I thought it was working. So you have magnetorotational instability developing here on the latitudinal gradient of omega. We have a strong effect of the Brine-Weisseler frequency of the stable stratification here that you see with the very small scale in the radial direction. And you see that this magnetorotational instability will develop either axisymmetric or non-axisymmetric in some other cases. You see again the very elongated structures in the latitudinal direction due to the stable stratification. And then what happens if you have this instability? Naturally, it will completely destroy your large-scale field you had initially, okay? Because the instability will create small scales in the radial direction, as we said, because of stable stratification. Small scales mean that you're going to have a lot of dissipation, and you dissipate your magnetic field completely. So this is interesting for application either for AP-BP stars or for red giants, because at the top, what you see is unstable cases, the radial field at the surface that you get when you have an unstable case and when you have a stable case. Remember that MRI is stabilized when the magnetic field is too strong. So at the top right, what we would think is that this is the AP-BP magnetism that we see, the large-scale dipoles, which seem to be stable. And the unstable case, if you think of spectropolarimetry, you're looking at this star, you have a lot of constellation of opposite polarities, and you're going to see a tiny field. So this would possibly produce some dichotomy between the two populations of intermediate mass stars. At the bottom, what I show you is the evolution, the nonlinear outcome of the instability for the differential rotation. And you see that, in fact, you're completely killing the large-scale magnetic field. And at the end, what you get is, again, differential rotation contraction, which is imposing the differential rotation it was trying to do at the beginning. So at the beginning, the large-scale field is imposing its flow. So we see almost no evidence of differential rotation. But then it's killed by the instability. So now contraction can spin up the core again. And this is what we can think of being related to the subgiant evolution, where we had first solid body rotation evidence, and then a little bit of differential rotation. Okay, so now dynamo action, because I haven't told you about this yet, but in fact, if you force a little bit stronger, okay, so now we force differential rotation on a short time scale so that you're not bothered too much by the effect of magnetic tension, which completely changes your differential rotation profile. You force, for example, with a body force, your differential rotation as a cylindrical profile, for example, this is an example, okay? And then you have the same ingredients. You put some initial magnetic field and you have stable stratification and you see what happens. So in this particular case, this is a simulation we've done with Domenico Mediori, who was a postdoc with me. And so you see at the bottom left, as a function of the amplitude of the magnetic field, x-axis and y-axis, the amplitude of the shear, you see that you have different behaviors. You can have MRI, yellow points. You can have Taylor instability, red points, and you can have MRI dynamo. These are the diamonds, okay, that you see, the two diamonds. You see on the right that we have a growth of the magnetic energy, and then we stabilize this magnetic energy. It means that we have dynamo action here. So what we can be interested in these dynamo action, in these dynamo calculations is the associated transport of angular momentum, okay? Yeah. So you see, you're producing real turbulence in these radiative zones when you have this dynamo action active. All right, so this is the MRI dynamo case. Now, I don't know if maybe you're not really aware of this, but there were also previous debates on the possibility that the Taylor instability could also trigger some dynamo action. So it was called the Taylor-Sproit dynamo, because Sproit is the first one who said that possibly there could be dynamo action relying on the Taylor instability. So there were previous debates because it was not really sure in numerical simulations that people were actually seeing it. It was still a theoretical argument at the beginning, but it's been revived recently by new developments. In particular by Petit Demange in 2023, and by people looking at in the context of neutron stars. So Paul Barrère in particular, 23-24. And so it's a bit of a tricky dynamo action because they need to, in order to find it, it's a bit difficult because they have to be in the right setup really. So it's a spherical quet setup, meaning that they're forcing differential rotation through the boundaries. The internal sphere is rotating at a different rate as the outer sphere. Okay, and in this particular case, what you see in the x-axis here is again the shear. So they force differential rotation more or less by rotating the two spheres at different rates. And on the y-axis is the magnetic field strength. And how they get this dynamo action is that first they trigger dynamo action by a kinematic dynamo. So they first have a hydrodynamical instability, which produces turbulence. Then it's okay, it's a basic thing. Hydro turbulence is going to twist and shear your magnetic field, produce dynamo action. And then the magnetic field is amplified until a time when it reaches the amplitude for the Taylor instability to be triggered. And then you jump on another branch of dynamo that for them is called the Taylor-Sprout dynamo. It's where the Taylor instability is actually playing a big role in the maintenance of the magnetic field. So I'm trying again. Yes, the green branch here is a Taylor-Sprout dynamo, but this is hemispherical. So this is funny because you find two modes of dynamo here, hemispherical one and a dipolar one. So you see, you expect to have action around the rotation axis. This is something which is true for the Taylor instability. And they have very strong fields. So the way then they keep, so something particular here also here is that when they decrease the shear below the value for which is initially started, they still find dynamo action. So it's a subcritical dynamo here. All right, so again, we can then be interested in the angular momentum transport by these two MRI or Taylor-Sprout dynamos. And in particular, since I told you that the stable stratification was bad news for these instabilities, we can wonder what happens in stars where the stratification is pretty strong. And if really the angular momentum transport can be important through these instabilities. So in fact, in the Taylor instability case, you can have scalings of the Maxwell stress, which is the main driver of the angular momentum transport here, as a function of n over omega, and you see that you have a power of -2, so this is decreasing pretty fast with the stratification. In the MRI case, we tried to have some scaling, which is not too easy with just a few points, but it seems less affected. We have only 1/2 for the power for the decrease. So this is promising for the angular momentum transport, maybe. Okay, I'm done. The conclusions are here. So I think there's a lot. I'm just not going to read all this, but I just want to tell you that I think there's a lot to be understood in these radiative zones, and we don't have the complications of turbulent convection, which is really great for numerical simulation point of view. I'm done. Thank you.
Thank you, Lauren. Very nice talk and very exciting results. So questions? DB and do.
Can you comment on the winds of these red giants? I mean, these fields are buried in the radiative zone. For the sun, magnetism does play in driving the winds. So for this red giants, would it only be a thermally driven wind governed by the heating in the outer expanding shell? Or would these magnetic fields actually have an impact on the winds in the red giants?
Okay, so so you're talking about here I'm talking about the very interior, the radiative core, which is in fact tiny compared to the extent of the convective zone, which they have huge convection zones, these stars. And what happens close to the surface, you probably still have a convective dynamo driving magnetic fields in this extended convection zone. So I'm not sure how you're going to have interactions between the contracting core, where you may have strong fields, and what happens in the convective envelope. This probably has to be studied in detail, because we have spectroparametric studies of the magnetic fields in the convective envelopes. So we may be able to have some, now we have measurements everywhere, you see. So there are great laboratories, these red giants, to do some very interesting science.
More questions? I have one question.
Yeah.
For your MRI instability, the dynamo produces a lot of turbulence. This turbulence doesn't kill the instability. How can the dynamo be sustained when you have all these?
All right, yeah, so you're talking about the, so what we do in these simulations is that we initially impose so we force a differential rotation, as you see here, and we impose an initial toroidal field, purely toroidal field, large scale. So there's an m=0 toroidal field to begin with, which is MRI unstable. And then it's still going to be around. This m=0 b phi is still going to be unstable to the MRI. So you're not actually killing the main ingredient for the instability to be here. So even though you have strong fluctuations, which are in fact quite stronger than the m=0 field, you still produce your instability.
No more questions? Okay. Thank you very much, Lon. The next speaker is Irina Kitiashvili. We'll be talking about
this request from online participants. Don't use laser point, and when you refer to some figures on your slide, please describe them, because they cannot see laser point. I don't know if it's possible to ask the point camera to instead of stickers.
Sure. Yeah, so remote participant, I know it is sometimes challenging to figure out what we are talking about. Yes, and during my talk, I'm going to discuss about effect of, no, we can, I don't have, I cannot really change slides. Oh, okay. So many confusions, great. Actually, I like confusions really a lot, because they drive us to understand something new by experience. And in this talk, I'm going to discuss effects of rotation, dynamic structure of upper convection zones of the sun, and also I will touch really also dynamics of stars, particular convection zones. And I just want to say, and I hope nobody leave from this room, but I'm going to discuss mostly about hydrodynamic simulations. I know it is no, so it basically means no magnetic field on most of slides. But reason actually I decided do so because we actually see many presentations yesterday, and today we also will see more about discussing interaction magnetic fields with rotation. But what I found actually, it is very important to understand how actually rotation act on structure of convective flows. And of course, it is no doubt about importance of rotation in terms of if we discuss about solar or stellar variability, about magnetic field generation. And but problem is if we don't understand how hydrodynamics affected by rotation, it is really hard to interpret it. And it is a lot of studies now is going on to perform modeling effects of rotation mostly in presence of magnetic fields. And most of them actually it is global simulations, but as we know, main problem with global simulations, they are not able usually resolve all essential scales, and they have have many problems in terms of reproducing in realistic way near surface layers. But of course, some progress made, and people start doing like simulations, including surface layers. And one of way to model these, to understand actually a coupling of rotation and convection dynamics is to perform models on local scales, and for instance, simulations bearing cut when many simulation box was included different latitudes and different regions of convection zone, but we actually suggest do a little bit different. We use existing computational capabilities to perform realistic simulations of near-surface layers, and we actually doing simulations only kind of upper layers of convection zone in case of sun. And for stars, we can actually model whole convection zone and radiative zone. Okay, so just as I mentioned, we do a lot simulations of stars, main sequence stars, more massive than sun. And the advantage of this, we can apply same developments, I mean, same or similar level of numerical treatment as we do for the sun and apply it to other stars. And because we really want to study whole convection zone, we do modeling for more massive star. For instance, on right, you see an example of simulations for 1.47 solar mass star. And the convection zone are pretty shallow, it is up to like 30 megameters deep. On background, you see fluctuations of temperature. And because star is more massive, we have really strong downflows, which reach up to 25 kilometers per second. And some of them just hit boundary between convection zone and radiative zone, and also generate gravity waves. But what reason why I decided to show this, because we actually, if we impose rotation in these stars, especially, for instance, in this case, I assume rotation rate for each latitude just 1 day, we see formation kind of like large scale structures. And interesting what such structures actually vary if we look at different latitudes. For instance, if you look on top, we see arrows show kind of mean flows in our computational domain. And we see formation of large elongated circular patterns. And with time, these patterns actually move, and sometimes you see substructures inside of them, but main structure remain in general same. Of course, with time it may vary a little bit. At 30 degrees latitude, we see what such large circulation patterns actually break on smaller one and getting more stable. And for if you go even further, like 60 degrees latitude, such circular patterns getting smaller and actually not very stable. And sometimes it is kind of like, it is up to me to say if I really see them or not. But what interesting about it, if you compare such results with global simulations, we see some similarity with well-known like teleproton columns modeled for different kind of type of stellar dynamics. And in general, similarity between these in our simulations, in some sense, we see kind of like columns, but structure of columns actually vary with the latitude. Okay, I try advance it a little bit. Yeah. So, and of course, it is interesting to discuss about differential rotation, but I would like to kind of warn you, it is in these simulations, we really cannot discuss about solar-like or anti-solar-like rotation, because by definition, I assume on all latitudes, I imposed rotation rate like 1 day or 14 days. So it is kind of like I can do whatever I like. I can make like a sol, anti-sol, it is up to me. But what is actually interesting about it, we see on, I try to figure out for people online, on left, we see differential rotation profiles. Oh boy, which direction I'm, okay. Oh, okay. we actually see how change rotation rate, how change azimuthal flows at different latitudes, and we see strongest deceleration of flows near equator, and actually such deviations getting smaller for higher latitudes. And also it is a lot of discussions about the gradient of rotation. For stellar case, we see, because it is much stronger rotation, we see very distinct and stronger rotational gradient for equatorial region. And for higher latitudes, it stays about same, and it is within the variations. And of course, it is expected as we have weak rotation, such discrete kind of variations in terms of differential rotation profiles and gradient of rotation gradient of rotation basically undistinguishable there. Yes, and what is going on if we discuss about the sun? And first, very important point, what I want you get from this talk is, even if we don't have any magnetic field, actually structure of turbulent flows vary with time. We usually discuss in terms of, yes, it is statistically kind of constant or not, but in general, structure changes all time. And it is, personally for me, really big discovery, because I start thinking if we start to look on solar variability, and of course, sun always have magnetic field influence. It is sometimes pose question how we're going to separate magnetic effects and hydro effects. And this example particular, we just assume for different latitudes we have same rotation rate. So it is, as you see, it is unrealistic. So we, in this case, in equator, we have quite suppressed turbulent motions, and see in middle, like 30 degrees, flows actually exhibit kind like wavy behavior. Partially it is because, of course, because we have box, and it is with periodic boundary conditions, but in general, it is it shows kind of like a periodicity which not always actually comparable with box size. And as we approaching to higher latitudes, we start see actually kind of signatures of polar vortex. Even in my box, actually my box have no idea about existence of polar region. And what is also interesting, we see differential rotation profile from this, and the differential rotation actually surprisingly quite consistent with observations. And it is more realistic case, and to impose rotation rate, we actually use global seismology data during solar minima. And in comparison with previous slide, like in equatorial region, we have a stronger rotation rate, and we see it is pretty stable simulations. But interesting, when we go to higher latitudes, we actually see some variations in flows. And you notice these simulations actually already hit up to 900 solar hours in simulations. So it is really very far from like initial conditions. And yes, and we actually start see very recently formation kind of like a new structure, and it seems like it is extremely stable and getting more consistent for different latitudes. And the gradient of rotation also actually suggests it vary with depth. and consistent and actually within published results from health studies. And I decided to include the plot for off-diagonal Reynolds stresses. And I think most interesting for these two things. First is we have quite substantial changes in structuring of flows as we pass go below roughly 8 megameters below surface, but also for different latitudes, we actually in deep layers we see kind of changes in evolution of flows, and evolution of flows actually show like we see Reynolds stresses basically propagate kind of perturbations to deeper layers, and it kind of like very I still thinking about the actual interpretation of this, but it looks like very stable. And I'm looking forward to look how it will change in presence of magnetic fields. But for high latitudes, we don't see really variations in Reynolds stresses, it's just like some quasi-periodic variations. Yes, and what is special about such layer, like roughly on depths 8 megameters below, we discovered it is leptocline boundary located on this, and I'm not going to discuss in details about this, and Jean-Pierre probably will discuss more about it, but main point of this, if you look on Reynolds stresses distribution, for instance, if you look on green curve, like horizontal component of Reynolds stresses on left, right, and you see strong variations, variation of this curve around depths 8, 10 megameters below surface. And similar, if you look on the right, it is anisotropy parameter. Anisotropy parameter shows actually how change Reynolds stresses when we pass such boundary. And it suggests actually we have kind of like weak overshoot layer. And this overshoot layer really weak, I should mention for this. It can, in some sense, it is similar what we have when we discuss about transition between radiative zone and convective zone. But it is such overshoot layer appeared because we have transition from more convectively unstable layers to less convectively unstable layers. So, of course, I still have convection below and above this layer. But importance of this layer actually suggests what it may contribute to process formation of magnetic structures and evolution of magnetic field. Yes, and let's jump back to stars and jump actually to meridional flows. I'm trying don't use meridian circulation because in box I cannot discuss this. And basically in meridional circulation for stronger rotation rate, we see, for instance, on upper left plot, for 1 day period of rotation, we have really strong variations in meridian circulation at the equator, 30 degrees. Oh, sorry, it is for high latitudes, and almost no variations from non-rotating case at the equator. And for, of course, for weak rotation, we have not such obvious variations in meridional flows profiles. Unfortunately, we cannot compare this with actual observational data, but we can do this for solar. For solar case, and for instance, on bottom you see profile for meridional flows, what we have from simulations. But keep in mind, even if I show this plot with very weak reversal flows in meridional circulation, in actual, this result kind of depends what kind of time period I choose in my simulations. Sometimes it is, I have reverse flows, sometimes not. But in general, qualitatively, if we compare these results with very different observations obtained with global heliosmology, we have a very good agreement in general shape of meridional flows. And again, if as already discussed about it, it is if you look on meridional flow components, for Carrington rotation rate imposed for all cases, we see, oh boy, why it is jumping. Okay, we see quite strong variations in flows from through different latitudes. And actually, as we go to higher latitudes, such flow patterns getting less stable. And again, if we discuss about case when we have realistic rotation rate, actually results getting more, how to say, sometimes more difficult to interpret, just because rotation rate for low latitudes, for higher latitudes are weaker, and time scales actually increase. Yes, and I want to touch a little bit effect of magnetic fields, and want to warn everybody when we discuss about magnetic fields, we usually in simulations use a constant Prandtl number, but in current simulations we really cannot resolve molecular Prandtl number, and on this slide I just want to illustrate some quite old small-scale dynamo simulations and the distribution of turbulent Prandtl number, what we extract from subgrid turbulence model, estimated from a subgrid turbulence model. And as you see, Prandtl number actually can vary by many orders of magnitude. About to finish this. And another important direction to study is to understand not just coupling of magnetic fields and rotation. And actually, I like a presentation from yesterday by Hannah when she demonstrated effect of rotation on the formation magnetic structures. But also, I believe it is important to consider coupling also with atmospheric layers. And I encourage take a look again, poster by Shrihana Roth. I hope I pronounced right. Because in this case, when we have magnetic fields, we actually have much more intense interactions of surface layers and atmospheric layers with strong also eruptive activity. And I would like just to show you key points and happy to take your questions. Thank you.
Thank you, Irina. So, questions, please. I do have a question. For you are showing not the actual velocity, but the residual or of the velocity.
Right, so correct.
Why is that?
Okay, simulations are performed in rotation frame. So, and if you want to get the actual one, it just kind of, you just add what was imposed, basically. Yeah.
And it seems that below a very thin layer, the convection is very stable. So you have strong convection just at the very top of the photosphere. Is that correct? And below of that, the convection?
For solar case, yes. We have strongest effect near surface layer, near surface, because it is downdrafts mostly occupy like first couple megameters. But perturbations actually going much deeper, and you see this from profile. Yes, important point what I want to mention for stars. Actually, we found because of shallow convection zone, we cannot form like a more complex fine structure of flows within a thin convection zone. So it looks in this sense more kind of like a single I don't know if it's correct to say single structure, so we don't see much substructuring of flows through convection zone for stars with shallow convection zone.
Any other question? Okay, thank you very much. Next speaker is Viggo Hansen. It's
Hello, everybody. I'm happy to be here. I'm a little bit surprised at finding myself in a dynamo session, but have patience, please. I will try to make the case that I belong here. So my starting point is that we have a basic idea of how coronal heating proceeds, and that is that we have a magnetic field in the photosphere, and it is being churned around by convection. And the basic idea is that we find flux everywhere. We have continual flux emergence. We have the field being recycled. We have mixed polarity. And then somehow this produces coronal heating. Okay, so being a modeler, I think let's take this idea and see where we go. So let's take a magnetic field, something that looks like this. And let's let convection churn it around. And we'll find a little bit of churning, which will lead to brighting. We also find a little bit of flux emergence because field is being reprocessed all the time. And indeed, we end up with a corona that looks, at least with this kind of view, pretty good. So now let's see what happens when we can compare what this model produces in terms of synthetic observations. Okay. Let's have a look at the coronal and let's look at the coronal counts. For one, yes, indeed, this corona looks really boring. But if we look at the counts we get and compare them with what we observe with AIA, we see that for all the 3 AIA channels where we get significant number of counts for the quiet sun, we get numbers that are roughly in the same ballpark as what we observed. So we're doing okay here. And at least good enough for me. If this was the only observable I had, I'd say, okay, I'm done with this problem. Let's move on to the next one. So let's move on to the next one and see what happens. Actually, first, let's say, what is actually heating this atmosphere? I haven't said that yet. And if we take a look, what it is we get braiding and we get small events happening, and that leads to heating. We get small scale, low angle reconnection going on. And this is essentially when we look at the spectral profiles of, for example, iron 9-171, we see something that looks exciting, and we're really looking forward to MUSE and to be able to see these kind of things going on or not. So let's move onward further down in the atmosphere. This is carbon-3, which I'm really looking forward to seeing with Solar C and the EU VST. And again, we'll see exciting line profiles and how the magnetic field, this kind of quiet, low intensity magnetic field, can actually lead to exciting events in the transition region. So yeah, we're looking forward to Solar C. And indeed, when we look at an IRIS observable, this is silicon-4, and the magnetic field at 2.5 megameters, we see that the points where we see excitement is where magnetic fields have gradients. And if we look at the counts and compare those with IRIS counts, we see that, all right, again, we're in the right ballpark. So, case closed. Let's move down to the chromosphere to see what happens there. So what does the IRIS magnesium-2 which is formed in the upper chromosphere, what does it look like? Well, we got a line core, which is pretty wide, about 50 kilometers per second in Doppler width. With the K2 peaks are well separated. And the K3 core is fairly deep. And we see a little bit of asymmetry. And we see that it is quite dependent on the size of the field. So the more magnetic field, the brighter the emission. And the average, well, let's go on. So let's compare that to our synthetic observations. Or rather, how long was Adam in paradise? Not longer than this. Because what we see here is that even though we get the intensities more or less right, there's a big mismatch with what's observed. And how do we fix that? Well, there's two ways of fixing it, or actually three ways. One is to say, you know what, Vigo, your code is kind of crap. It's way too diffusive, and you're doing observations at 100 kilometers resolution, which is pretty bad. So your spectral lines are going to be thin, and as soon as you improve either your diffusivity or your resolution, then it's going to get better. For example, we had the same sort of problem with calcium-2, which is formed a bit further down in the chromosphere. And when we went from 100 kilometers, where you see here where the line widths are way too small, and we go to 30 kilometers, how? The line widths get bigger. So clearly there, in that case, the fact that we have better resolution leads to better or more turbulence in the model, and then wider line widths. Okay, so why not test that, see what happens with the magnesium? And with the magnesium, let's test what happens when we have 100 kilometers, which is the model I've been showing you, and let's compare it to 50 kilometers. And here's the difference. It doesn't do much. So this may not be good enough, or this may not be the source. And in fact, when we go even better down to 4 kilometers, which is kind of getting on the almost ridiculous, we still don't approach the observations, the observables. So maybe we should look for a different way of increasing the line width. And now I'm finally getting close to the question of why am I talking about dynamos at all? And the question then is, at least for me, is, okay, I'm doing a box and I'm putting it in a star, and I'm going to try to do the quiet sun. And then I start wondering, what is the definition of the quiet sun? And to do that, then I have to think about, okay, what kind of field components should we consider? What do we include in a box in a star simulation? And we have a lot of stuff going on. We have supergranulation, we have granulation, we have sunspots that are being moved around by the meridional flows, diffusion, and so on. And how do we actually define a region? What is a quiet sun, for example? And just to show you this example, here's the sun, one rotation before the image I just showed you. Here's the spot I just showed you. One rotation later, it's starting to get ripped apart, and another, and another. And if I want to put a box in here, where do I put it? And which components of the field do I include? Because my magnetic field is a free parameter that I have to put in here. All right. So with that in mind, let's now think, we've been reading Matthias Rempel's papers, and he says there's a lot of local dynamo action going on. So what do we, and that should lead to flux emergence. What if we increase the amount of flux emergence we have in our model? So let's go back to our original simulation. Let's pump in some magnetic field and see what happens. And here's just a movie of that. All right. What happens now with our simulation? And I've picked out two boxes here, a red and a green one, where the fields are pretty weak. So I can imagine I take these two postage stamps and make models of them. Let's look at what happens to the magnesium-2 profiles. Here is a little bit later, and pow. Even though those boxes are in regions where the field is pretty weak, still, we see that we get profiles that are very similar to what is observed, even though we're still at 100 kilometers resolution, which is pretty crappy. So clearly, the entire scene that we're looking at is going into setting what the width is. And what is happening is that we're putting more material into the chromosphere because of flux emergence, and that is actually affecting the line widths in places even where the fields are not strong. So when we're making models, for example, of the quiet sun, we really have to be aware of what is going on in the magnetic topology in the entire area around where we're in. And I think that is more or less the end of what I had to say, because I only had 10-15 minutes. So thank you.
Thank you, Vigo. Very interesting. Questions, please. Oh, there is one.
Christoph Petroway. You need to assume some kind of a spectrum for this flux emergence for scales?
In my case, I'm just putting in a sheet of magnetic field at the bottom, which is 8 megameters below the surface. So I'm not sure quite what you mean by spectrum. You mean spatial or?
Size. So the different sizes of these emergences.
No, the emergence is a sheet that covers the entire box.
So it's produced by your convection.
So it's split up by convection, yeah.
Okay.
Vigo, I assume the magnetic field you put in the box is horizontal initially, right?
Correct.
And does it reach the chromosphere easily? How is it possible? Because it's a very weak field, right?
It takes a while. It has, I mean, what I'm pushing in, are you asking at which stage? It piles up just below the photosphere, and there's continual action. And in places where it does pile up enough, then we reach, I guess it's Atchison, we reach this limit, and we get strong enough that it does go through into the chromosphere. So there is continual flux emergence going on, and some of that field, not all of it, but some of it does reach the chromosphere and carries a significant amount of mass. And if you look at the profiles of the chromosphere and the temperature structure, you'll find that it does not resemble the Val3C model. The chromosphere is much more extended, and I think it needs to be. And this is maybe another takeaway of this talk, is that the chromosphere, in order to reproduce the upper chromosphere, you need to be quite a bit more extended than what the Val3C model is telling you. I don't see how you can make the widths of magnesium-2 as wide as they are observed to be without doing that.
There is an online question.
Hi.
Emily.
Hi, thanks. Although I haven't had a chance to see the first part of the talk, I would still like to take this chance to ask you whether you have any guess or perspective or any plans to try a simulation of bigger scale flux emergence into an active region and its effect on the chromosphere in a similar way of material going up and so on.
I am doing simulations with stronger fields and also slightly different geometries. But to be honest, I prefer doing geometries that the sun sets, and it's not really obvious how and what sort of structure of the field one should have in order to do a realistic simulation. And I guess this is an open question. It's open to me, at least.
Loading.
Yeah, I have two small questions. First one is, does your result depend a lot on the amplitude of the sheet that you're imposing, or did you try to vary this magnetic field strength, or not so much?
Not so much. I have not varied much, so I can't answer you properly. I would say it doesn't really matter, but then I would be lying because I don't know.
Okay. All right. And the other question is that I'm not sure I understood if you do have a small scale dynamo action in your box, or the question is, do you really have to impose this sheet, or could you have natural dynamo action producing what you need for your
I think personally, for the Bifrost simulation, at least at 100 kilometers, the dynamo that it produces is pretty wimpy. But I know that the Muram simulations, where they have less diffusion, it's less diffusive, they actually have a better small scale dynamo or local dynamo, and there they get closer to what is observed. So I think in principle that if the story for modelers is you need to go deep, because as Matthias said a couple of days ago, or was it yesterday? I don't remember. Anyway, you have to go fairly deep in order to reproduce what is observed. And you have to go fairly deep, and you have to have fairly good resolution in order to have your local or small scale dynamo be effective. But Whether the 60 Gauss that they produce is good enough to match the observations, I think that's a question that's still slightly open. I.e., whether or not you need to couple also to the global dynamo or global fields.
Okay, let's thank Diego again. The next speaker is Ryota Shimada. I hope I am pronouncing well. So please.
So hello, I'm Ryota Shimada from Kyoto University, and I'm going to talk about the mechanism of stellar activity rotation relationship driven by the turbulent angular momentum transport. So first of all, let me clarify the target of our study. So there have been recognized there is the activity rotation relationship for cool stars. And one of the prominent example is shown in right top panel here. And horizontal axis is Rossby numbers, and vertical axis is observed surface averaged magnetic field strength. And this Rossby number is defined by the period of rotation over the convective turnover time. And we can find the stellar magnetic field have a systematic dependence on its rotation rates. And also there is the saturation-like behavior occurs at extremely low Rossby numbers. And target of our study is why such saturation of the field strength occurs. And why this is important is that the stellar magnetic field regulates the stellar rotational evolution via magnetized stellar wind, and it originates stellar magnetic activity which should affect the planetary atmosphere. So one of the proxy of stellar magnetic activity is shown in right bottom panel, and horizontal axis is again Rossby numbers, and vertical axis is normalized X-ray luminosity, and we can find the similar systematic dependence on rotation rates. And here I briefly touch with what are found by stellar dynamo simulations. And here I show one of the state-of-art 3D global image simulation performed by Brun et al. 2022. And they investigate the dynamo action in several types of cool star with different rotation rates. And the covered Rossby number is from 0.18 to 3.9, and it's not overlap with saturated regime. And here I showed one of their results. So here the horizontal axis is Rossby numbers, and vertical axis is field strength of magnetic dipole component. And this magenta line is the best fit of their results, and this dashed line is from Zeeman Doppler imaging observation. And we can find the Rossby number dependence of large-scale dipolar magnetic field before the saturation is reproduced. However, it is very difficult to access the extremely low Rossby number stars by 3D global MHD simulations. But there is another option to investigate the extremely low Rossby number stars, which is the local Cartesian simulations. And recently, Capilla 2024 performed the hydrodynamic local Cartesian simulations. And left top panel shows the snapshot of their vertical velocity field, and right panel showed their convective velocity. And here, the horizontal axis is Coriolis numbers, which is the inverse of the Rossby numbers, and the vertical axis shows the root mean square velocity. And we can find that in extremely low Rossby number regime, the velocity and the length scale of the convection decreases with rotation rates. And this gives rotational dependence of the turbulent viscosity as following form. So here I describe the purpose of our study. As I mentioned, the global MHD simulations obtain the consistent scaling with observation in moderately low Rossby number stars. And on the other hand, local Cartesian simulation reveals the property of turbulent convection in extremely low Rossby number stars. So here I consider what can be said from these informations to observed saturation. So our purpose is to probe the possible mechanism to saturate the field strength in extremely low Rossby number stars by utilizing recent information from global and local simulation. And our method is nonlinear mean field dynamo model. So here I explain our nonlinear mean field dynamo model. So in this model, we solve the axisymmetric flow field and magnetic field. So by doing so, we can include the nonlinear interaction between the axisymmetric flow and magnetic field. But on the other hand, we do not solve the non-axisymmetric flow explicitly. So the effect from non-axisymmetric flow is modeled by lambda effect and turbulent alpha effect. And the lambda effect is a bit complicated, but important for our study. So let me explain further. So if there is the anisotropy induced by the Coriolis force, then each component of the non-symmetric flow is correlated like this schematic picture. And this can carry the angular momentum equatorward. And this physics is modeled by lambda effect. And here, the turbulent viscosity roughly represents the strength of the turbulence, and here rotation rates roughly represent the coherence produced by Coriolis force. And here I demonstrate our free parameters. We changed the rotation rates of the star from 1 solar rotation rate to 32 solar rotation rate, so we can include the saturated regime. And turbulent diffusivities are also free parameter, and we use 3 different diffusivities. And in left panels, we show the examples of our simulation. And here I show the butterfly diagram at the base of the convection zone. And here after, I'm going to discuss the data which is taken temporal average over this period. And in order to compare with the observation, we define the average magnetic field as this formula, and we perform this integral at the base of the convection zone. And left panel shows the Rossby number dependence of our average magnetic field for fixed diffusivities. And our field strength is proportional to the Rossby number to minus 0.5. And in the bottom panel, we show the result from global MHD simulations. And here we show the magnetic energies. And we can find that our scaling is consistent with 3D global MHD simulations. And here in middle panel, we show the viscosity dependence of our average magnetic field for fixed rotation rates. And by combining all results, then finally we obtain the free parameter dependence of our average magnetic field as this form. And here I'm going to discuss about what determines this scaling relationship. And in the top panel, I show the snapshot of magnetic field and butterfly diagram. And at the bottom panels, I show the snapshot of differential rotation and the butterfly diagram of rotation rates. And we can find there is significant nonlinear interaction between them. So for a better understanding of the mechanism to determine the field strength, the analysis on pairing of differential rotation is necessary. So I perform the analysis on energy equation of differential rotation. And here, this term represents the acceleration by turbulent angular momentum transport, and this term represents the deceleration by turbulent viscosity, and this term represents the deceleration by Lorentz force. And temporal evolution of each term is shown in this bottom panel. And we take the temporal average of them and compare with different cases. And here is the result. So horizontal axis is again Rossby numbers, and vertical axis shows the absolute value of each pairing terms. And if we look at the faster rotating case, then the acceleration by turbulent angular momentum transport, these blue dots, and deceleration by Lorentz force, these green dots, are dominant and have similar dependence on Rossby numbers. And this suggests that field strength for fast rotator is determined by balance between the turbulent angular momentum transport and Lorentz force. And in order to quantitatively understand the scaling index, we perform the dimensional analysis of each pairing terms. And after some manipulation, finally we obtain this scaling relationship. Here we insert our rotational dependence of differential rotation. And if we assume the balance between turbulent angular momentum transport and Lorentz force, then finally it gives this scaling relationship as this form, which is obtained in our simulation. And here I'm going to discuss what can be inferred from our results. What we obtain is this scaling relationship. On the other hand, recent local Cartesian box simulation indicates that the turbulent viscosity have rotational dependence like this for fast rotating case. So by combining these two results, then we finally obtain the Rossby number dependence of average magnetic field for fast rotator as this form. And the impact of this is shown in this right panel. So here, again, the horizontal axis is Rossby numbers, and vertical axis is the average magnetic field, and these dots and these blue lines are from our simulation with fixed diffusivities. But if we take into account the rotational dependence of turbulent viscosity, then this blue line fell into this magenta line. And this index is very close to the observed index. So here I summarize our work. So our purpose of this study is to probe the possible mechanism to saturate the field strength in extremely low Rossby number stars. And our method is nonlinear mean field dynamo model. And our pre-parameter is rotation rates and turbulent diffusivities. And we obtained the consistent scaling with 3D global MHD simulations. And our field strength is scaled by this form. And finally, our conclusion is that field strength at deep convection zone is determined by turbulent angular momentum transport, and inefficient turbulent angular momentum transport in extremely low Rossby number stars can be the candidate of the field saturation. So that's all for my talk. So thank you for listening.
Thank you very much. So, questions? Several questions.
Very nice talk. Thank you. I was wondering, which expression did you use for the lambda effect? Was the one from Günther Rüdiger, which has the rotational quenching in there, or what did you assume?
So we do not include any quenchings. So here is our formulation of the lambda effect, and we do not implement the quenching of turbulent viscosities, and we use the similar spatial distribution of the lambda effect as Lempel 2005.
That's a nice result. So I was just wondering, did you look at the profile of the differential rotation with the Rossby number and see if it changes from the solar light one? And also, could you comment on if you see meridional circulation in the simulations and what happens to it when you have a very fast rotator?
Okay, so yeah, we check the profile of differential rotation, and here is our differential rotation profile. So differential rotation profile is shifted from solar-like to the Terra-Proudman-like differential rotation. And here we do not put the profile of the meridional circulation, but for fast rotator, the strong meridional circulation is shifted to lower latitude.
So just for broader application, on this graph, magnetic field strength as a function of Rossby number, fully convective stars, like young MA sequence stars, are also located on this saturation locus, and they're fully convective, so they're powered by convection-driven dynamos. Just for broader application, I was wondering if you thought of how it could be explained by fully convective saturation rather than just the alpha omega saturation. Have you thought about it?
So yeah, I'm thinking about the extension to the lower mass stars. But one of the problem of our model is we assume the distribution of the lambda effect. So if I want to extend, then it is necessary to know the information of the Reynolds race for low mass stars. And also, yeah, if there is only the turbulent alpha square type dynamo, then this mechanism also work is, I have no answer with them at this moment. So yeah, so thank you for your comment.
Last question. Hi, nice talk. This is Travis Metcalf. Just your comparison with the Bruin simulations, it seemed like the field strengths were different by a couple orders of magnitude. I just wondered if you had an explanation for that, or did I misunderstand?
Okay. This panel. So here they show the magnetic energy density. So we cannot directly compare with these results. And here the strength of the magnetic field is taken at the base of the convection zone. On the other hand, the field strength I showed here is taken at the middle of the convection zone in various simulation. So I speculate the difference is come from the depth.
Alexander Kosovichev, I'm wondering how you define the Rossby number, because the convective velocity changes by orders of magnitude in real stars. So what's the meaning of this?
So in order to circumvent the misleading, so I define the Rossby number for stellar Rossby numbers, which is used in observation. So here the Rossby number is from velocity computed by the mixing length theory.
The Rossby number changes with the radius.
Yes.
How do you define here the Rossby number?
For the Rossby number at the base.
Okay, let's thank again. And the next speaker and the last speaker in the morning is Adriana Value. So please go ahead.
Okay. Thank you, everyone, especially for sticking up to the last one. I have like 6 minutes before the end of the session, so I'll try my best. I'm from the Center of Radio Astronomy and Astrophysics, Mackenzie, that's in São Paulo, Brazil. And I'll try and give you on this talk parameters from stellar parameters that you can use in dynamo simulation, in dynamo calculations. So, of course, we know sunspots on the sun, and they're the first indicators of solar activity. And we believe that all convective stars also have star spots. And we also know that the stellar activity decreases with time or age. So in the top panel, you have here stars of different ages, the younger stars on the left and the older one on the right. And you can see there, here is the light curve of the photometry showing that the period increases with time as the star ages. And before the launch of Corot, I realized that we could infer the properties of star spots during a planetary transit. So when a planet crosses in front of a dark feature or a bright feature on the surface of the star, in the case of a star spot, we can see a bump, and that's what you're seeing on the left panel. And on the right panel are two simulations of a Jupiter-sized crossing planet and an Earth-sized crossing planet. And you can see the difference here, and don't be fooled. Here is the difference from one to another is 100 times in depth. Okay, so what am I talking about? What I'm talking about is a model that I developed in 2003. And you can see the planet here crossing, and there's the transit. The star is a 2D pixelated image, and the planet is a circular, dark region, and with a radius, with respect to the stellar radius, the orbit can be elliptical with its parameters like semi-inclination, semi-major axis, inclination angle, and period. And the spots is characterized by basically 3 parameters. Its intensity, size, position, and in the intensity or temperature. And then the position is usually the latitude is fixed, which depends on the transiting of the orbital inclination of the planet and its semi-major axis. And you can see here what the kind of structure it produces on the transit light curve. And here's an example for Kepler-17, 3 spots, and you don't really see that much here in the transit light curve. That's the top right panel. But when you subtract a spotless star model, which is the dashed blue line, I don't know if you can see it, but here in the bottom right panel, you can see the 3 spot signatures that have been modeled. So this was done for about 13 stars. But before we go into that, how do I estimate the rotation or its differential rotation? And well, basically we have to see the planet transit the surface of the star, transit 2 different transits. And here is a simulation, and we can see 2 solar images on 26th of April and 29th, separated by 3 days. Here's an active region. And here you can see the 2 transits. One is in black and the other one is in red. And you can see that the spot has an apparent relative move, like in phase of the transits. And from this difference in phase, you can estimate the time it took, not the time, the difference in longitude. And so you can estimate what the rotation period at that transit latitude is. So, and here's just an example. This is a simulation just to show you how this works. So here is one star, and you can see that it's O because I've done this first, like 2013 with Corot 6 star. I distributed 4 spots at different latitudes, all at the same latitude, but different longitudes through 12 transits. And you can see here the signal of one of these spots. Okay, so now how do I estimate the differential rotation period at that latitude? Well, you have to convert it from the longitude that we see here from Earth to the longitude that is on a rotating reference frame with the star. So in order to do that, here is the equation that you can translate from the topographic latitude, that's what we see here from Earth, to a rotation longitude. And all we have to do is vary the rotation period. And so, but before we do that, I do what I call the stellar surface map. So after modeling all the spots that I see in all different transits, I put the spots here and I stack all the transits, so it's longitude on the x-axis and time or different transits on the y-axis. And there you can see the tracks of the 4 spots. And so I start with the period, rotation period that's smaller than the average period that we can measure from Lomscargo, for instance, of autocorrelation function. And you can see here the line. So I just change the rotation period on that equation. And you can see that the inclination of the lines change as well. And I just continue to increase or decrease, if that's the case, until voila, I find vertical lines. What that means is that all the spots are aligned. And so I'm really seeing the same spot at the same rotational longitude on the star. And this is the rotation period of the star at that latitude. And okay, so from then, how do I estimate differential rotation? There are 3 ways that we can do it. If we have multiple orbits, That's the case of Kepler 411, and we've done that because they had like 3 transiting planets at 3 different latitudes. If we have inclined orbits, it's much harder to do it, but it's possible. It's been done for 2 stars. Kepler 63 is an almost polar orbit. And the most common case, which is just 1 planet, and we assume that the orbit of the planet is coplanar with the stellar equator. We assume a solar-like profile, differential rotation profile, and for that, we have 2 constants, which are 2 unknowns, A and B. A is the equatorial rotation, and B is the shear, or that is the difference between the rotation of the equator and the poles. And we have 2 measurements of these, or actually what we measure is 2 periods. We have the average period, which is what you get from the overall light curve from using Lomskargel. And we also get the rotation period at that transit latitude, which is the method that I just showed you how to do it from the stellar maps. And so we have 2 unknowns and 2 measurements, omega 0 and omega 1. So we can determine these 2 constants, and that's exactly what we've done for these 13 stars, which are active and have transiting planets. And you can see that the stars go from F, G, K, and M type stars. And on the left side of the table is the stellar parameters, and on the right side is the transiting planet. And these are the numbers that we got in the last column, but better than showing you as numbers, I'll show you them as plots. And so what we plotted here on the left is the shear, the rotational shear, that is the difference from the rotation from the equator, from the equator to the pole as a function of the rotation period, and which is also maybe an indicator of age. And on the right panel is that same quantity, the rotational shear, as function of effective temperature. And what we see here is that there is a good anti-correlation between the rotational shear and the rotation period of the star, and a very weak or basically no correlation between the rotational shear and the effective temperature of the star or stellar masses. So those are the ingredients that I propose to you who want to model, like stellar rotation for stellar dynamos, I'm sorry. And here are the different parameters for different stars. And so for my conclusions, I have shown you how I can estimate the rotation period at a transit latitude using planetary transits, and combining that with the average rotation and assuming a solar-like profile. We found that for 13 stars, which range from K to M spectrotypes, we found a strong anti-correlation between the rotational shear and the average rotation period of the star or its age, and the weak correlation of this same rotational shear and the effective temperature of the star. And thank you. And if you want to know any more information, well, here's the GitHub for the Eclipse code, which is the code that I use for modeling and fitting the star spots on the transits of the stellar light curve. Thank you so much.
Thank you, Adriana. We still have time for questions.
Thank you, neat talk. My name is Hannah Shunker. I have a general question about these stars. Is there any information on the activity cycles or the amplitude of activity on these stars?
Yes, there is a paper, Estrela and Value. I think it's 1916 or 1918, which talks about the stellar cycle that we got from the Kepler 63 and Kepler 17. Of course, Kepler only observed those stars for 4 years. So we're limited to short cycles, and we got cycles which are about 1.3, less than 1.5 years. Might be what we see, the quasi-biennial cycles that we see on the sun. We're not saying that that's the full cycle, because for that, we would need a longer observing time. But yes, just by counting the spots on each transit as a function of time, we can get, like we can really do a star spot numbers plot and see what the cycle is like.
Hi, Ariana. So there is
Hi.
some observations which indicate that the sun, as it ages, doesn't slow down as fast as it should. So the rotational braking sort of breaks down at some point. Is it possible to apply your technique to much more older sun-like stars to see what happens, or is it very difficult to do that?
No, even for stars, the age of the sun is already difficult. Why? Because we need, I mean, the way we spot, the way we identify the spots is from the activity in the light curve. And I mean, and a curve of a solar-like star would be very flat. And not only that, but the spots are much smaller because these are huge spots. Usually, of course, maybe they're not individual spots, maybe they're like active regions, but they're like almost 10 times the size of what we see on the sun. So very hard. I mean, maybe, I don't even know if Plato will give us the precision for that photometric precision because they're not very active, the spots are small, so it's very hard to detect.
Hi, Travis Metcalf. The correlation, anti-correlation that you found between the rotational shear and the rotation period, I noticed that it goes close to zero by the rotation period of the sun. I'm just curious how the relation that you found compares to other, say, ground-based observations to determine the same.
Oh, okay. Well, the sun, it's about zero. It depends, I mean, on how you measure it, but there was this nice compilation. Oh, I forget the author now, 2020, maybe. I don't, well, it's 0.02. So what happened with the, well, you can go to the edge of the plot. That would give about, you know, like the rotation period of the sun, with about 27 days. It's the average one that we consider, and 0.02. So, and another thing is that this is not, I apologize, the latest version of the plot, you know, like we did a log for that. And because it's not really a line, if you fit, you know, like an exponential, a decaying exponential, it fits much better. The correlation coefficient goes up to 0.9. And then it doesn't go to zero. But you see that the sun is not too far off from, if you consider the spread, 0.02.
Small question, Lorenzo. I was wondering if your results were very dependent on the profile that you're using for the different rotation. You're using a solo-like?
Yes, I don't know. I'd never tried another one. I'll be glad to use another one if you can give me.
Yep, for the fast rotators, you may expect cylindrical profiles. So I don't know how much it changes for the surface. Maybe
Okay.
sine only.
Okay, so can I look your publications? Will you have them there? Or
I don't, but we can discuss.
okay. I mean, I have the two measurements, so I can fit any curve as long as it's just two, parameters. Yep. Even anti-solar rotation, that can also be arranged. It doesn't always fit. Sometimes you get, I mean, not all stars, you won't be able to fit for all stars with an anti-solar. I haven't found any anti-solar yet. Because those expect to be old stars, right? I think that's what the
So we have an online question. So is there enough evidence to see difference in a spot width with a stellar spectral type?
By spot width, do you mean like spot size? I don't think so. I think they're basically just, well, I don't know if I can. Oh, here, maybe. Oh, no, that's the plan. I don't have the average parameter of the spots here. So, I mean, I haven't looked at it yet, but I don't know.
Any more questions? Thank you, Adriana.
Thank you.
It's time for lunch. Sasha, you do have something to say now? Any info? No? Okay.
Okay, hello. We are going to start the next session. So before, for the speakers, there are some participants online, so they are not able to see laser pointer. So when I make presentation, use laser pointer, but same time describe, what you're showing these pictures on the left, on the right, top, bottom, and that upper curve, lower curve, something like this.
So should we start? All right. Good afternoon, everyone. So next session, we have exciting talks for this afternoon. So the first talk is Shibata-san. So please go ahead.
Good afternoon. At first, I'd like to thank organizer, especially Kosovichev-san, for inviting me to this conference. This is my first time to come to South Africa, farthest country from Japan. It took more than 1 day to come here. Okay, I will talk about this subject. And this is today's plan of my talk. And basically, at first I talk about introduction to super flares, and then introduce you a very new discovery of a filament eruption from a super flare on young solar type stars. Also, more recently, Dr. Namikata discovered the evidence of prominence eruption from also super flare on young solar type star. That will be a very important hint for a future disaster from solar super flares. So I think very important. Maehara, I'm sorry, I made a mistake, name, Maehara. It was 2012, using Kepler data, revealed that not only young solar type stars, that is G-type main sequence stars, but also old slowly rotating solar type stars show super flares, which is defined as the flares with the energy 10 times more than the largest solar flares in recent 40 years. That is, super flare energy is from 10 to the 33 erg to 10 to the 35 erg, roughly corresponding to X100 to X10,000 in Gauss X-ray class. And left panel is the typical evidence of a superflare observed by Kepler Space Telescope. Vertical axis is the stellar brightness in unit of the average brightness of a star. And the horizontal axis is a time, day, for roughly 30 days. And you see the stellar brightness itself change with time, with amplitude roughly 1%. And you can see some spikes. These are superflares. And biggest spike shows 0.015 stellar brightness. That means 1.5% brighter than average of stellar brightness. Please remember, even the very largest solar flares brightness is 0.01% of a solar brightness. So therefore, this brightness is more than 100 times larger than the largest solar flares in recent 40 years. And total energy is estimated to 10 to the 35 erg in this case. And right panel shows a hypothetical image of this star showing a very big spot. Because stellar brightness change is probably due to the existence of a large spot with a rotation. And these observations are made by visible light continuum, visible continuum. So so-called white light flares. So if we see stellar surface, we would see such a very large white light flare. So you can imagine if this occurred, what would be a extreme disaster on the Earth. So people are interested in the effect on exoplanet atmosphere around the young sun. So important for astrobiology. And also, this is very important for future of the sun and the Earth. So we discussed superflares occur on the sun or not. So, and furthermore, as I explained in the today's plan, can superflares produce a huge mass ejection and affect the planet around the superflare? This is a very important question. So today I will mainly talk about that. And this is initial data from Kepler data. Vertical axis is a flare energy, and the horizontal axis is a spot group area from time variation of stellar brightness. And but in the case of solar flares, of course, we can observe the spot size. And upper data are from Kepler data. And you can see there is common tendency from lower left to upper right. And this is because flare energy come from magnetic energy stored near the spot. And if spot size is large, we have a lot of magnetic energy stored near spot. So larger spot produce larger flares, super flares. So you can understand that all super flares occurred in a very big spot. And now we have more data between two. Recently, both data are connected, solar and stellar. And so can super flares occur on the present sun? I'm a basically theoretician. But when I was young, I was doing MHD simulation, but now I can use only my hand and pencil. So this is the order of magnitude theory. And this equation is basically the Faraday's induction equation. phi is a total magnetic flux in a toroidal direction. And delta omega is a differential rotation of the sun. And phi p is a poroidal magnetic flux. And poroidal magnetic flux can be amplified by a differential rotation and estimated as this formula. And from this equation, we can calculate necessary time to generate magnetic flux of 10 to the 24 Maxwell large spot observed in previous superflare stars that can produce superflares of 10 to the 35 erg. And we can estimate the years, 40 years. And this is much shorter than the average frequency of necessary time to wait superflares. But this is, of course, larger than 11 years. So people may think this may not occur. But in order to produce a 10 to the 34 erg superflare, we need only 8 years, which is shorter than 11 years. So from this very simplest order of magnitude estimate, I can say that I cannot reject this possibility. 10 to the 34 erg superflare cannot be rejected. So this is a very scary result. But of course, today and yesterday, as people discussed, we need a more developed dynamo theory simulation. So this is a big challenge to dynamo theorists. And from Kepler data, before that, we already know solar flare frequency decrease with increasing energy in a power law. And if we plot the superflare data from Kepler, interestingly, in the same line. So from this, we can say that superflares of 100 times more energetic than the largest solar flares occur once in 6,000 years. So this is long, but this is comparable to the time scale of a very big earthquake occurred in Japan 10 years ago. So we should be serious about this value. And the question is whether these superflares on stars are similar to solar flares. And solar flares often show gigantic mass ejection and mass ejection prominence filament eruptions and coronal mass ejections, which impact the Earth and produce magnetic storm and disaster. So stellar flares also accompanied by mass ejection. This is a very fundamental question. And Dr. Namekata, my last student in Kyoto University, my last PhD student, used a 3.8 meter Seimei telescope in Okayama in Japan, a very new telescope. Using this telescope, he discovered evidence of a filament eruption. That is, left panel shows, left upper panel shows a continuum time variation from TESS. That is a white light flare. And lower left is H alpha intensity observed by 3.8 meter Seimei telescope. And at first, H alpha emission occurs at the same time as the white light flare. But after impulsive phase, H alpha shows dimming. And that is probably absorption, like filament eruption shown in a hypothetical image, the right panel. And middle panel, lower panel shows the upper panel shows the line profile in H alpha. You see emission and absorption H alpha line, and middle lower panel shows the wavelength versus time. We call dynamic spectrum. And red is emission and blue is absorption. And interestingly, Doppler shift decrease with time, roughly comparable to the gravitational deceleration. Oh, sorry. And Dr. Namekata compared this stellar data with the solar filament eruption data taken at Hida Observatory of Japan, and found a similar event. You see here H alpha movie. Black is a blue shift, white is a red shift. That is the filament erupt and the material fall along the field line. And the dynamic spectrum is quite similar to stellar dynamic spectrum. So Namekata et al. Concluded that this is the evidence of a filament eruption. And the maximum velocity is 500 kilometers per second. So he concluded this would evolve to coronal mass ejection. But Referee and many stellar astronomers argued this is not evidence of a CME because the velocity is less than the escape velocity. But I think as a solar physicist who know observation very well, this filament eruption is a good evidence of a CME. Usually filament velocity is much smaller than the CME, but the CME can be produced. And I'm a theoretician, so I tried to make a simple model for time variation of H alpha spectrum filament eruption with ICTA. And we performed a one-dimensional hydrodynamic simulation of the flow along the expanding magnetic loop, emulating a filament eruption using self-similar model of CME, like right lower figure. And so we solved the hydrodynamic equation along this field line. And so this is a very simple model. So we have only several parameters. So easy to study parameter survey, much simpler than full 3D MHD simulation. And this is a result. Left upper panel shows theoretical dynamic spectrum. And the left lower panel is from observation. This is the solar case, solar filament case. And nicely reproduced. And this is also, this filament also finally becomes CME. And you can understand because magnetic group itself continues to expand, even the filament material fall along the field lines. And the same model was applied to young solar type star EK Dra, and again, very successful. And this clearly showed magnetic group itself continued to expand, become CME. So I'm sorry, I don't have enough time, but Namekata found another evidence of eruption, but in this case, emission. So this is probably prominence observed at the outside of the rim. And from solar data, we also ought to analyze such a similar dynamic spectrum. And very similar to stellar data. And again, ICTA modeled this very nicely. And this is a stellar prominence model, very similar to famous prominence eruption on the sun. So I don't have time, but important result is mass energy relation is found for CME. And our finding of a filament prominence eruption is on the same line. And furthermore, Notes et al. Analyze a M-type star flare, super flare. Then found a similar tendency for mass and energy relation. And this mass and energy relation is found from simple order of magnitude estimate, flare energy and CME mass. So we found this is a very universal law. Okay, so this is the summary. Maybe I should stop. Thank you very much.
Thank you very much. So we have time for questions.
Hi. So AK Draconi, it has age of between 50 million years to 100 million years. Relative to Prime sequence stars that I've talked about yesterday, this is quite old star. You call it young star for the whole audience. For us, it's old star. It's already developed alpha omega dynamo. It works like the sun. Flares are much more powerful than on the sun, but much less powerful than on real Prime sequence stars.
Yeah.
So for me, as a Prime sequence astronomer, it's interesting to see if you are able to point your telescopes Ash alpha and make Ash alpha observations of real Prime sequence stars, so very young, located in, for instance, Orion Nebula cluster. Is the possibility, but Prime sequence stars, of course, they undergo various types of variability. There is accretion takes place, and in Ash alpha, there's accreting stars on Ash alpha. It's huge, but you can just choose diskless stars with no accretion, very young, 3 million years old. Is it possible to perform such an experiment, what you did for AK Draconis? And because Prime sequence stars, they have much more, the frequency of detecting very large flares is, they're much more frequent in producing powerful flares than AK Draconis. And you will have chance to, to detect more.
Thank you very much for very nice advice. And I want to send your comment to my young colleagues. And actually, I have been stressing the importance of observation of Prime sequence stars at Okayama new telescope. And we have an observational plan this year and next year. So please wait for a moment. Yeah.
There is a question online. So Emily.
Hi.
We cannot hear you.
Yes, now you can hear me. Sorry.
Yes.
Yeah. Just to comment on this question, actually, a few years ago, in a detailed study of EK Draconis, including detailed abundance analysis from spectroscopy, we had found that the age of EK Draconis is around 30 million years, putting it to a much younger age. And of course, you can see the study, but in that sense, it might also be actually younger than 50 million years. So my question is, actually, I have a comment on magnetic flux, toroidal magnetic flux storage and intensification near the base of the convection zone. So your estimate about the required toroidal flux timescale for intensification is based on differential rotation only. But we know that from 3D MHD simulations and other studies, 2D studies and so on, that there are other sources of mechanisms for intensifying toroidal flux near the base of the convection zone as well as in the bulk of the convection zone. So maybe it will be easier even. I don't know in fast rotators, but yeah. So
yeah, thank you for your comment. And if someone will collaborate with me, dynamo theoristician, I would be happy. Okay, and in relation to this, I want to show one slide, backup slide. This one. This is our Kepler data, flare energy versus rotation period of stars, solar type stars. So EK Dora rotation period, probably 2 days or so. So as a first person commented, we want to extend this to further left. And the point is, even solar rotation, we have super flare. So this is a very important, not only for our modern society, but also for astrobiology problem.
Okay, thank you very much, Shibata-san, for such a great talk. I don't know if you're aware, but we published a paper. The first author is Simoes, S-I-M-O-E-S, in 2024, in January, talking about the estimate of the flare energy. Instead of assuming a constant 9,000 or 10,000 black body temperature, we calculate from the Balmer lines of solar white flares, and we usually get energies which are a little bit smaller. If you allow me, I'll send you through email a copy of that paper. And now the question, do you have an estimate for the energy of the Carrington event?
I'm not, but I know several papers. And recently, Hayakawa et al. Published the Astrophysical Journal letter. He concluded the X class, more than 100. So previously, 40 or so, but he carefully analyzed the sketch of Carrington and concluded that the possibility of maximum value is 126x. Yeah.
Thank you, Shibata-san. My comment is that from extreme solar-energetic particle events observed in the past millennia, we do know that something extreme happened on the sun, probably super flares, but more important, that would be extreme or super CMEs. And what you found, or your colleagues find on the stars, would be very important for our sun to know how the extreme solar-energetic particle events are formed roughly once per 1,500 years. So we do know that something weird happens on the sun, very rarely, but it does happen.
Yeah, thank you for the comment. And I also prepared unrelated, this one. This is from already published paper, Takahashi, Mizuno, Shibata in 2016. You see the left is a CME speed scattered diagram, and the right is a proton flux scattered diagram. And the dashed line is the theoretical upper limit from order of magnitude estimate. And today I discussed the possibility x100, x1000, maybe likely. So that tells you possible largest proton flux and the largest CME speed. But that is extreme.
Oh, thank you very much for the presentation. And for dynamo theory, important not just rotation, but also metallicity and stellar mass. So do you have some plots how it depends on metallicity?
We have not yet studied, but that is another interesting, suggestion. Yeah, I hope to study it.
Okay, so thank you very much. Very nice talk.
Thank you very much.
Now it's Stefano Belloni, please go ahead.
Sorry, which one?
That's the slides, and this one if you want.
No, it's fine. I'm gonna flail. It's fine. All right. Hello, everybody. My name is Stefano Bellotti, and I'm a postdoc researcher at Leiden Observatory. And first of all, thank you very much to the organizers for giving me the opportunity to present my work, which is in particular about magnetic fields of stars and activity cycles. So at this point in the week, I don't really have to go too much into detail about this plot, of course, but just briefly, this is basically a compendium of magnetograms that have been longitudinally averaged, and we see the evolution over time, over a bunch of cycles. In particular, we see the emergence of magnetic spots around plus or minus 30 degrees, and then they converge towards the equator as time goes by. And around activity maximum, the polarity of these spots reverses in something that we called overall Schwabe cycle. And then in order to restore the same magnetic configuration, we need 22 years, which is more the timescale for the Hale cycle instead. On the large scale, as I try to depict at the bottom of the plot, the magnetic field is predominantly poloidal and dipolar at activity minimum, and then it reverses, of course, polarity every 11 years, and around activity maximum, it becomes more complex. So for this crowd, I don't really have to push too much into the motivation as to why studying activity cycles. But of course, the sun is an important benchmark because we want to understand and predict what is going on in terms of magnetic fields and evolution. But it's one data point. So we also need to understand the magnetic fields of other stars and their evolution to properly contextualize the solar dynamo and to provide the test beds on which to test our theories. And I also want to point very briefly at an interesting synergy that there is with the exoplanet community, because the magnetic fields of stars dominate the environment in which exoplanets are embedded, and these environments are modulated with the magnetic cycles of stars. So the story I want to talk about today is basically a brief summary of the various techniques and results that have been proposed to hunt for activity cycles. And in particular, I'm going to use the sun as our benchmark because, of course, it's the most studied star. So I'm going to try to go through all of these briefly. Yes. The first method that comes to mind, at least in my mind, is the chromospheric heating modulation. Because as a matter of fact, if we look at the calcium HNK lines, the calcium ionized HNK lines, just a bit blueward from 400 nanometers, we see the emission reversal in their cores, which is a symptom of activity of stars, of magnetic activity. So we can compute the S index, which is basically the ratio of the flux in these lines, in the core of these lines, with respect to the bolometric luminosity of the star, and we can monitor it over time. On the sun, we see that this is correlated with the sunspot cycle, as shown here at the bottom. And then this was performed extensively for many other stars. We have the Mount Wilson project in the late 60s that found several stars showing these periodic variations in the S index and revealed stars that have pretty much similar cycles to the sun, or with longer or shorter timescales, with similar shape, or even more chaotic and more irregular cases with perhaps even the superposition of multiple cycles. And the more stars we obtain, the more we can start to see trends in these in the activity timescale, basically. So, for instance, we see that the rotation period, that the cycle period is correlated with the rotation period, and also with age, in the sense that young stars tend to have more irregular cycles than older stars, like the sun. Another method that comes to mind, and it is very similar to the chromospheric heating, is the coronal heating modulation. In this case, it's not observed at optical wavelength, but in the X-rays. And what we look for is the modulation of the X-ray luminosity over a long time scale, pretty much. So it has been done for the sun, and it has been seen that is correlated with the S-index cycle, but we also can do it for other stars. The only problem here is that X-rays observations are expensive in terms of well, money, because we need to send spaceships in space, and also in terms of time. So, because in order to find these cycles, we need the right baselines in order to capture the modulations of these quantities. And therefore, most of the stars that have been observed having X-ray cycles are also known to have chromospheric cycles. So they were targeted already with known cycles. So of course, photometric modulations is also like a direct way to hunt for cycles, because the magnetic field is responsible of surface heterogeneities, and it modulates their presence over the over the cycle. Clearly, this is a primary method. On the sun, clearly we see this modulation, which is also correlated, and it's I'm stressing the fact that this is correlated because these are all phenomena that all proxies that converge together, and they're kind of synchronized, even though we're using multiple techniques. So in this case, it's also correlated with the S index. When we look at other stars, basically we look at variations in brightness, periodic variations in brightness for these stars, and results have shown this has been applied extensively for FGK stars and also M dwarfs. And the results I'm showing here on the right, at the bottom right, from Reynolds and collaborators 2017, show that from Kepler data, there were a lot of stars showing periodic variations. And in particular, the density of the observations is pretty much agreeing with what we knew from chromospheric activity, basically seeing that the cycle period correlates with the rotation period of the star. And then there are also other cases, like the sun, where the chromospheric index cycle is synchronized, or kind of correlates with the brightness index. With the brightness variations. And so these are even more solar-like cycle cases, so to speak. There is also asteroseismology, which is going to be very important in the light of Plato, as I'm going to show also later. Basically, what happens is that in the interior of stars, we have oscillations, p-mode oscillations, that are, whose frequencies and amplitudes are affected by the magnetic field. So if the magnetic field changes over the cycle, we also see the frequency and the amplitude of these oscillations to change. We see this on the sun, of course, but we also see it on other stars, as shown here on the right. And and we have a correlation or an anti-correlation, basically depending also on what kind of proxy you're using, whether it's the amplitude of the frequency itself. In terms, this was also performed for many other stars, and in particular, I tried to summarize here some of the main properties for which the maximum frequency variation was computed over other fundamental solar parameters. And we see that most of the active, or let's say fast rotating stars, or younger stars have higher frequency variations. The maximum is higher, and so there is this correlation, and also with temperature. Now, another method is spectropolarimetry, which is something I personally work on. As I said at the beginning, the large-scale magnetic field on the sun is simple at activity minimum and complex at activity maximum. The plot on the top right shows the measurements of the solar wind at these different stages. It's not really the large-scale magnetic field, but I really like this picture, and it kind of conveys exactly what I want to say. On the bottom right, instead, we have the sun as a star magnetic field reconstruction provided by Alina Vidotto and collaborators in 2018, where we see how we would reconstruct the magnetic field of the sun over the solar cycle 24. So this has been done for the sun, but it also has been done also for other stars. And this is basically also where I come in. I use the Zeeman Doppler imaging to reconstruct the magnetic field of stars. This is a tomographic inversion techniques with which we basically take polarized light data, and we invert this time series into a map of the large-scale magnetic field. And on the right, I'm showing an example of a map which is decomposed in the spherical coordinates components, the radial, azimuthal, and meridional. And the color indicates the polarity. In red, it's positive, and in blue, it's negative. These are polar projections, meaning that the pole of the star is at the center, and then we have concentric latitudes going towards the equator. Going outward, and the equator is the solid line. So this is one reconstruction for a specific solar-like star that is kind of a solar analog in the sense that it rotates around 22 days. If we do this for more observations over like with a yearly cadence, pretty much, this is what we obtain. I'm going to focus in particular on the radial component. As you can see, at the beginning, the magnetic field was predominantly positive, then it flips to negative for 3 epochs, and then it flips back to positive again. So over the course of pretty much 10 years, we have 2 polarity flips, which could hint at the fact that this star has a magnetic cycle, a Hale cycle, that has, it is twice as fast as what we see on the sun. So I've been doing this for this star, but also for a bunch of other stars that have similar mass to the sun, but different rotation periods, to pretty much see the impact of the rotation period on the topology evolution of the field. Finally, I wanted to briefly mention a couple of methods that haven't been used much or that could sort of show potential for future detections of magnetics and activity cycles. One is the flare occurrence rate. We know that on the sun, the flare occurrence rate is modulated with the solar cycle. And so it will be interesting to see that also for other cool dwarfs, although there are some signs already that these are coming out. And then there's also polarized radio emission. Radio emission can be polarized, and therefore it can be sensitive to the sign of the magnetic field at the source point that it was originated from. And with that, we can sort of trace magnetic polarity reversals. This has been done for ultra cool dwarfs, but to my knowledge, not for solar-like stars. Finally, I wanted to briefly mention like synergies with Plato, in the sense that Plato is going to be, I'm really excited about Plato because this is a photometric mission that will allow us to potentially hunt for activity cycles, both using the photometric and the astereosismology method. These plots shown on the right are from Breton and collaborators, and they show injection recovery tests of light curves with certain activity cycles timescales. And you see that despite the nominal length of the mission is 4 years, if we manage to get it extended to, let's say, 6 or to 8 years, the reliable recovery of these activity cycles would be much more significant. Nevertheless, even if we only have 4 years of observations, it will be able to sort of see shorter timescales observations, phenomena such as the Rieger cycles or the flare occurrence modulations, as well as the quasi-biennial observations. And I think I will stop here. I basically wanted to just point out that I tried to count the number of stars with the detected cycles, tried to put a kind of a ranking over here. These can be considered as lower limits because maybe I missed some. But yes, it will be interesting to see a lot of methods also kind of getting more and more data to provide an interesting synergy between these multi-techniques. So with that, I'll stop here, and thank you very much.
Thank you, Stefano, very nice talk. Another here.
Hi, with regards to magnetic cycles, so we just recently did analysis of very young stars, primi-sequence stars. So far, we cannot find magnetic cycles, at least X-ray activity cycles on those stars. But I've read the literature a little bit, so there was a challenge to finding cycles on fully convective M dwarfs, low mass, late. I found in the literature several papers. They still sometimes they're not sure if they're fully convective or in the borderline between fully and. So the main challenge is, do we know if stars that have convection-driven dynamo produce magnetic cycles? So for you, it would be interesting to have samples of late M dwarf stars and try to figure out this science topic. I don't know, for instance, spectropolarimetry, if they have enough signals to target those late dwarfs.
Yeah, so basically, there is this work from Rout and collaborators 2016 that they go even like very ultra cool dwarfs, and then they see this polarized emission flip. So it could be a hint of magnetic cycles. But if we look at spectropolarimetry, I myself worked on M dwarfs as well, and I had I recently published a paper with sorry, shameless self-promotion, a paper with a fully convective star in it, and over a time scale of, what was it? 12 years, it did not show a magnetic topology evolution. Although there was, I have to say, there was a huge gap in between the observations, but from 28 to 2019, the topology was exactly the same. So I don't know, that's the thing. Yeah. That's, well, yeah, no, that's a good suggestion. I would need to see, if they're visible, signal to noise ratio, all that stuff for spectral polarimetry. Yeah.
Oh, thanks for the very interesting talk. Do you have kind of catalog of stars on your last slide?
And the last slide.
When you counted that, do you
Yes.
have a catalog of these somewhere?
No, I counted basically. So I basically counted the number based on what they were saying in the results section, or maybe the abstract, or all the papers I could find about cycles. So I don't have the names of the stars. Yes, I have the name of the papers where I took the numbers from, but I don't have the name of the cycle, the name of the stars.
There is one online question. So Emery.
Hi, thank you, Stefano. How do you actually get the polarity change from radial field maps, I suppose? But since the resolution is rather coarse, do you actually look at the dipole component? And if so, do you actually also plot the dipole component, how it varies, and how significant is the conclusion that we are actually observing a polarity reversal?
So I'm not sure about the topology that they assume from the radio observations. However, as far as understood, the radio emission, it comes
No,
from...
excuse me, Stefano, what I said is not radial component of the magnetic field.
Oh,
So
sorry.
in your maps, there's a polarity reversal going on that you showed, right?
Yes. Sorry, then what was the question again? Sorry.
Then the question is, how do you actually how reliable is the conclusion of a global dipole reversal of the magnetic field? I mean, do you actually look at the time series of the dipole moment that you calculate somehow, or you just visually, or yeah?
Yeah, there are different ways. One thing is also to compute the longitudinal magnetic field, so the disk integrated large-scale magnetic field, projected on the line of sight. And there you see that the bulk of the observations is positive at some point, and then it becomes negative, and then positive again. But also from the circular polarization datasets themselves, you see that the shape of the circular, the Siemens signature flips across different epochs.
Okay, yeah, thank you.
Right, so with the ZDI technique, typically we always see this very large-scale coherent distribution of a patch, like a positive polarity or negative polarity patch, which is pretty large area coverage. I've always wondered, is that a resolution issue where you're looking at sort of an average over multipolar distributions, or is it really that large-scale unipolar patch that is in the star?
No, it's a resolution issue in the sense that we are limited by how fast the star rotates. So the faster the star rotates, the better spatial resolution we could have. But for these kind of stars like the sun that are slowly rotating, that's what I mean by large scale, like only what survives on global scales.
Thank you.
Thank you.
Next speaker is Luis Balona. So please go ahead.
Well, in the Kepler and the test stars, you see a large number of stars with rotation periods typically of 1 day and very low amplitudes. And if these are cool stars, you could of course interpret this as possibly due to star spots and where the period of rotation is the same as the photometric period. But what I'm talking about here are A and B type stars. This is an entirely new class of stars, not really noticed because the amplitude is so low. In fact, you can see there, those stars, the periodograms I'm showing here have amplitudes typically of 100 parts per million or less. And there are about 7,000 of these stars now known, all A and B stars. So the question arises, what is the variation due to? One can think of various mechanisms. Pulsation springs to mind, of course. Shallow eclipses, tidal effects, or star spots. But of course, star spots are not supposed to be present on these stars. Simple test you can make is to take the stars for which the projected rotational velocity v sine I is known, and you can plot the v sine I against v, which is the assumed rotational velocity at the equator, using the photometric period and the radius. So the graph would look possibly something like this, with most of the stars lying below the straight line, which is v sine I equals v. And if you do this, this is what you get. These are the stars right from 6,000 Kelvin to 30,000 Kelvin, all the early type stars really. And you see that they agree more or less with this assertion that the photometric period is a rotational period. But of course, this kind of graph could be obtained if a large number of the stars maybe have slightly longer periods. So a better test would be to compute the distribution of stars with v sine I for a particular effective temperature band, and do the same thing for v, and compare the two. Now, there would necessarily not be the same distribution if there's a spread of photometric periods different from the rotation period. You only get the similar, very similar distribution if the rotation period is a photometric period. And this is what you get from the observations. And indeed, you see that in every case, the distribution of stars that you get from v sine I and from v are pretty much similar. And that it can only mean that, in fact, the rotation period and the photometric periods are pretty much the same. Does this, so this indicates that if you take, say, pulsation as an explanation for this, then the pulsating star has to have a period which is the same as the rotation period. What this means really isn't a pulsation, it's just a distorted star which is rotating, that's all it means. On the other hand, you could say, well, maybe the periods are slightly different from rotation. Then you can invoke inertial mode, perhaps. This was done, in fact, some years ago by SIO, and there were, in fact, very convincing demonstrations that you can get inertial modes very close to the rotation period, but in the stars they used, there's a very sharp peak to the a slightly shorter period, which they can only interpret as the rotation period. So what I'm saying is that although inertial modes are possible, the rotation period is still there. So you can't explain everything just by simply inertial modes. Now, here's another graph which shows the distribution of amplitudes in these stars. And you can see they're all very low amplitudes, all of them below 1 millimagnet, 1 part in a thousand. And they're all, the number of stars decreases with amplitude. Now, that's very odd. It's difficult to explain other than something like star spots. If you take, for example, these could be planets, then you have to explain why do the planets have always the same rotation, orbital period as rotation period. In any case, if these are planets and periods around about 1 day, they must be extremely close to these extremely hot stars. They probably wouldn't exist, they'd be vaporized. So you cannot explain this by planets, perhaps a small star of some kind, but then this will cause tidal effects. But you might notice something quite peculiar about this graph. All the stars, all the A stars, stars below 1,000, have very similar range in the amplitude there that I've shown. They go from 0 to 1. But among the B stars, the amplitude goes from 0 to 3 for the late B stars, and 0 to 10 for the early type stars. This is something unexpected and rather peculiar. There is a simple explanation for this, but I don't think I have time to explain, but perhaps towards the end of all. This is a demonstration or an easy graph to see what I'm talking about. You see that stars cooler than about 10,000 degrees have very low amplitudes, but all of a sudden, for the B stars, the amplitude shoots up tremendously. And we have to understand why is this. Now, you might think, let's go back to the possibilities that we've discussed. We've discussed so far pulsation, which I think we can not entirely eliminate, but very unlikely. We've discussed the question of planets or other small bodies, maybe with shallow eclipses, but we've seen that this can't be the case because the stars would be planets will just not exist, such close proximity to the stars. And if there were a small star like an M dwarf, you'll have tidal effects of some kind. Let's look at the possibility of tidal effects. If the stars are close together, the distortion of the star will be large, so the amplitude will be large. At the same time, the orbital period will be much smaller, and so you'd expect the velocity, the rotational velocity, v, to be larger. In other words, you'll expect a correlation between the amplitude and the v that you get from the photometric period. Well, this is a graph you get, and there's no correlation. So this cannot also be due to tidal effects in stars. So one's left with the only sensible explanation that makes sense, and that's rotation, and that's star spots in rotating star. Now, if that's the case, that means A and B stars must have localized magnetic fields. If they have localized strong magnetic fields, you expect flares. So one possibility is, can you see flares in these stars? Well, in fact, you do see flares. Here they are. These are flares in A stars from Kepler. But if you think about it, this is rather strange because A stars are hundreds of times more luminous than K and M dwarfs. And so if you have an M dwarf next to an A star, all the flares there simply won't be seen. They're totally overshadowed by the extremely luminous star. And so these stars really need to be super flares. They have to have extremely high energies. The energies of these stars, and in fact, this is an HR diagram from Kepler, which shows the distribution of flare stars across the diagram. And you can see they go all the way up to the early A stars. So this is confirmation that whatever you like it or not, flares are present in A stars. Now, some of you might think, well, surely this could be due to cool star, which is flaring, the cool star orbiting the M star or the A star, which might be flaring. If you work out the energies of these stars, these flares on the A stars, they came out to be larger than 10 to 34 ergs. And about 2.5% of all the A stars flare. That's an enormous percentage because the number of super flares on K and M dwarfs is extremely rare. They're 1 part in less than 1,000 or 10,000. So you've led to the conclusion these flares cannot possibly be on cool dwarfs orbiting the star. It must be on the A star itself. And so this is further confirmation that these stars are very active, and they need to have, in order to explain these observations, you can only understand it by assuming that these have very strong localized magnetic fields. And so my brief conclusion is that there are new horizons to be explored. One has to break away from the idea that stars in radiative equilibrium are forbidden to have these magnetic fields. There's something wrong with that. You have to think of some explanation which allows for these magnetic fields. Otherwise, you cannot explain these observations. And that has further implications, because implications perhaps for pulsation models, but particularly for models which seek to explain chemical peculiarities in these stars, because they demand that the atmospheres be very static, etc. And so these things have to be revisited. Now, I think I have some time to explain why the strange thing about the amplitudes rising sharply in the B stars. Now, for this, I have to say a few words about the BE stars. These are normal BE stars in which H alpha emission is present. And this alpha emission is due to the circumstellar disk. The star has episodes of outbursts in which mass is expelled into surrounding disk, and this is what causes the emission. Now, these are some of the light curves you see from BE stars, and they all show the three peaks, typically very low frequency peak, which is probably due to the circumstellar disk, a peak somewhere around a cycle a day, which is close to the rotation period, and another peak at twice the frequency. This can be understood if during an eruption, the clouds hang around at more or less a location of the eruption, and as a star rotates, these clouds will act like a big star spot and obscure the disk periodically, and you see these variations. Now, what is the reason why you get these amplitudes? Well, you would presumably find stars for which the mass loss is much less, and the velocity does not reach escape velocity from these eruptions. And so they will appear as a normal B star, but they will still have these rotational modulation, because the expelled clouds of gas will still be obscuring the star. So this will be indistinguishable from these other stars I've been talking about. They will appear, again, as simple normal stars with rotation periods of a day or so. So what I'm suggesting is that here you're seeing a mixture, in the B stars, you're seeing a mixture of two different mechanisms, if you like. You're looking at star spots, which have low amplitudes, and these active B stars, which are not emission line stars, but still have eruptions, and which cause this variation. And since the obscuration from the circumstellar clouds is much larger, you get much larger amplitude. And since the number of BE stars or BE phenomenon increases rapidly towards the hot stars, then this will explain this, this particular thing. So that is the end of my talk, really, and thank you.
We have time for questions.
Hi, I'm Dave Soderblom from Space Telescope, and about the flaring A stars. You correctly regard the possibility of having an orbiting M dwarf as not plausible, but the A star is luminous, so how far away are they typically? There's something like a kiloparsec?
Well, I'm looking really quite bright stars. Sirius, for example, is an A star. It's only 8 light years away.
No, Sirius is not in your flaring sample. The Kepler stars that are A stars, aren't they typically a kiloparsec?
I'm not, these are bright stars. I'm looking at stars brighter than 12 magnitude. That's my absolute limit.
I know, but
so they're all
so
within a few, I would say within a parsec. I mean, 1,000 parsecs. Yeah, kiloparsec.
That's a kiloparsec, yeah.
Yeah, probably.
So
yeah.
the postage stamp for Kepler, from which the photometry is extracted, is pretty good sized. It's not a square arc second or whatever.
Yes.
So my point is there's a substantial volume of galaxy between
Yes.
us and these stars. And if you look at the density of very, very low mass stars in the immediate solar neighborhood where we can actually detect them, it's very plausible there's a very low mass star, and every one of those cones, that's a foreground star.
Correct, that's quite possible, but that's not the explanation, because if these were indeed foreground K and M stars, they'd be very close to us, right? These are bright stars, as I said, bright in 12th magnitude. We're missing about 200 of such stars with large proper motions. Are you telling me that, you couldn't see that?
The foreground stars are invisible to us because they're so darn faint. That's why we have a hard enough time detecting them out to 10 parsecs or 20 parsecs.
What I'm saying is it's not possible to explain flares by optical alignment of a cool dwarf with the A star. That's what you mean, isn't it?
Yeah, and why is that not possible?
Well, because, as I said, if you have a 12th magnitude star in line of sight within 2 arc seconds, and you have 200 of them, all exactly lined within 2, that's a field of view of Kepler, the aperture, 2 arc seconds.
No, the postage stamps are much larger than that.
I know, but I've looked, there's nothing around these stars. There's nothing around
I
these
know
stars.
they're invisible. They're very low mass stars. They're totally invisible to us, and they could be the things that are flaring.
Maybe we can get the discussion for.
And you say these, to me that doesn't sound plausible, but thank you.
One more question.
Luis, thanks for a very interesting presentation. If you look at the light curve, Kepler light curve, then flares, they often appear without signatures of star spots. In star spots, you should see darkening and then flare. And my second question is, can you rule out R modes in these variations? Rossby modes, R modes?
So what?
Rule out R modes.
Oh, R modes. Yes, well, R modes is what I'm not an expert on R modes and that type of thing, but R modes don't create flares, do they? I mean, you have to explain these flares.
Oh, you have one question.
Yeah, I was wondering if you had these super flares only from AP BP stars, the one which are strongly magnetic, or you see also them on more normal A stars?
Well, you see super flares on G-type stars and K-type stars.
Yeah, I mean for the ones you say that you have some flares on A stars, right?
Yes.
So these are not the ones which are the strong dipoles, the AP BP stars.
No.
No.
In fact, I think there's only one star among the AP stars which I noticed a flare. They're very rare on the AP stars for some reason.
So that's intriguing. Okay.
Yes.
Okay, thank you very much. So next speaker is Paulo.
Hello?
Is online? Okay.
Can you hear me?
Yes. Yes, please go ahead.
Let me try to share my presentation. Do you see it?
Not yet.
Not yet. Now?
Okay. Yeah.
Does it work?
Yeah,
Okay.
it's small, but we can see the
Better?
presentation, but it's very small.
Now?
Now it's better.
Now it's better. Okay. So first of all, I wish to thank you, the organizer, for giving me the opportunity to talk about this connection between solar and stellar magnetic phenomena through the observation of white light flares. In particular, I will describe some recent works about the series of solar flares observed on the Sun in September 2017. And first of all, I want to remark that the most energetic solar flares up to 10 to 32 erg are dynamical phenomena involving the whole solar atmosphere, with important effects also at photospheric level. And during these events, electron beams, characterized by particular high energy, reach the chromosphere, which in turn, owing to its radiative heating, stimulates the photospheric emission. And this heating mechanism is known as backwarming effect. Thanks to the high spatial resolution of the new generation telescope, we know that the white light emission is present not only in the strongest events, but also in lower class flares. And however, the more energetic is the flare, the more detectable is the white light contribution, which is concentrated in a form of several kernels, which probably correspond to the Lookfoot points. In this movie, using exceptionally high resolution images taken by the New Solar Telescopes at Big Bear Solar Observatory, we see the ribbon propagating across the sunspot, the appearance of more and more post-flare loops, which are filled with condensing chromospheric plasma, and the chromospheric plasma following towards the loop and producing this white light emission. The Kepler emission, as Shibata-san said, has recently revealed the occurrence of extremely energetic flares, named super flares, with energy up to 10 to 37 hertz, several orders of magnitude higher than the solar flares. And this Kepler observation showed that these super flares occur especially on G-type dwarfs, and the occurrence rate of super flare versus flare energy shows a power law distribution with an exponential alpha equal to 2. In the case of sun-like stars, the most active stars shows a frequency of 1 super flare with an energy of 10 to 34 erg every 100 days. Observations have demonstrated that the characteristics of these events, apart from their total energy, do not differ significantly from the largest solar analogs in terms of duration, temporal profile, and so on. However, the average magnetic field strength of young stars is higher by an order of magnitude than that for the Sun at maximum in the modern era. I can say that a disadvantage of a simple scaling approach is that to explain the super flares, one needs to assume that the area occupied by spots is very huge. I can say also close to the whole stellar surface. And super flares seems to occur more often on cooler and faster rotational period stars. And these are some typical example of strongest solar flares, solar events. For example, in the images on the right side, you can see the famous Bastille Day flare, where the emission at different wavelengths it could be ascribed to a reconnection site very low in the solar atmosphere. And various observations support the idea that this continuum emission at photospheric level may be correlated with low heights of the reconnection site in the solar atmosphere. I consider this particular most powerful active region, super active region, 12673, which appeared on the Sun at the decline phase of the cycle 24. Within 1 week, this super active region produced more than 4 C-class flare, 27 M-class flare, and 4 X-class flare. Among these events, we observed the strongest flare of the cycle, an X9.3 flare, and the active region was characterized by this delta spot with several umbre inside the same penumbra. The main characteristics of this active region is the extraordinary values characterizing the emerging phase of this superactive region. The flux emergence rate peaked on September 3rd with an extraordinary value of 10 to 21 Maxwell per hour, which is the greater value than any value reported in literature. And here we can see 2 of them, 2 X-class flare. They are really interesting because they are recurrent homologous white light flares. If white light flares in the Sun consist of rare events, homologous white light flares are even more rare and exclusive. And the homology of these 2 white light flares is demonstrated not only in the similar morphology at chromospheric level, as you can see in the ribbons in the middle panels, but also in the brightening of the coronal magnetic systems involved by the events. Here, the contours indicates the hard X-ray sources at observed by RESI in the 1225 kiloelectron volts energy band, and these are considered usually as the source of the main magnetic reconnection, and they are located in the center of the delta spot. Here you can see the white light emission in the X2.2 and X9.3 flares. Of course, the area reached a total maximum extension proportionally to the energy delivered by the two events. And these effects are also visible in the magnetograms acquired by HMI. Here you can see on the left panels and in the right panels the running difference in the continuum and the magnetogram respectively. And you can see also the location of the hard X-ray emission corresponding to the more or less the center of these two ribbons in the polarity above the polarity inversion line. And the main results in this case is regards the measurements of the horizontal velocities. In this case, we see we used Dave for Buchem, which is an algorithm which is able to track the patch, the magnetic structures at photospheric level, and we detected that the negative polarity indicated in black in these plots, in these maps, showed a very interesting northward displacement, which was observed for more than 24 hours with an average velocity of 0.5 km per second and some peaks of 0.7 km per second. And this shearing motion is important because it has been observed for more than 24 hours. So we have this persistent peculiarity in the shearing motions. And probably this is the source of the injection of magnetic helicity into the corona, because has been observed an helicity due to the shearing motion 4 times higher than the helicity due to the emergence of new magnetic field. In order to reconstruct the 3D coronal magnetic field configuration, we adopted the nonlinear force-free field extrapolation method proposed by He, Wang, and Yan in 2011. And we used as input the 2D photospheric vector magnetograms for the extrapolation. And what we observed is the presence of two 3D null points, which are usually considered the source of the magnetic reconnection, where the particles are accelerated downwards. And these two 3D null points were located at low heights above the photosphere, about 5,000 kilometers and 3,000 kilometers for the X2.2 and X9.3 flare, respectively. So their formation at such low altitudes may probably be ascribed to these peculiar photospheric horizontal motion I showed before. And this is our summary and conclusions. What we observe is the stretching of the magnetic field lines, or at least we can say that we observe the strong shear, which could be the source of the stretching of the magnetic field lines, and which is able to put down the height of the 3D null points. And considering that the super flares occur in very fast rotational star, we argue that a possible explanation of the acceleration of huge numbers of particles producing white light emission during super flares in young stars could be the occurrence of magnetic reconnection at low altitudes of their atmosphere. So these two ingredients, the fast rotation and also the low altitude where this reconnection takes place should be investigated in details. Regarding the sun, our next step is to consider this active region, which appeared a few months ago, which was responsible for several aurora observed on the Earth at low latitudes. In this case, we observed this temporal order of process, a flux emergence, then the converging motion, which made this active region really compact, similar to the active region of the Carrington event, and then the shearing motion. In the longitudinal component, we observed this in this J map, where we plot the velocity in time. We can see this black and white corresponding to this opposite direction of the velocity fields at photospheric level, which can justify the shearing. And we are performing now the magnetic field extrapolation in order to find the location of the possible presence of 3D null points. So our idea is to extend our sample to consider more solar events and to consider these events. Finish it. And to consider these events as possible hints to interpret the superflares. Thank you for your attention. That's all.
Thank you. We have time for maybe one quick question. No questions? Okay, so let's thank Paolo again. And the last talk of this session is Saida Milena Diaz. So please go.
Okay, so, well, thank you so much for the organizer of this focus meeting to give me the chance to present this work here. And also I want to really make a great thanks to the General Assembly organizer to make this event in first time in the African continent. So happy to do that. So I'm going to show you today this work that I developed with my collaborator. And this is a really nice example of how the small scale dynamo acts and in the smaller scales and the lower solar atmosphere. In this case, I'm going to show the multi-phase small scale magnetic field amplification in a vertical structure. Okay, so I'm going to show you a little bit of the introduction, the data and the methods. So, as we know, the solar surface and the solar photosphere is full of magnetic field concentrations. And if you saw, for example, a magnetogram of this solar disk in the center in this region, you can see how this magnetic flux is organized at different scales in the granulation. At this moment, Vigo shows that the quiet zone regions usually harbored an aberrative and involved magnetic field organized at these different granular scales. So you can have like this flux emergence organized in the regions of the intergranular lanes, where most of the flow is going inwards to the convective zone. Usually these are accumulated and are observed as bright structures in continuum images or in specific bands of the spectra as the G band. What's the important things in this small scales magnetic field concentration? Usually in the smallest sizes below 1 arcsecond sizes, the experiment amplification of the emission of this flux will be affected by the turbulent convective flows. So there was a specific work done in 2020 by Peter Keyes that he studied the mechanism of this rapid amplification of the magnetic flux in such scales in a turbulent convective flows. He shows that the merging of surrounding magnetic field accumulation is the most common process that happened and usually feed up the network regions. The second one is the compression due granular expansion. Usually this makes that the magnetic structure get compressed and deform and also increase the magnetic flows locally. The magnetic, yeah, the one of the most studied one, it's the convective collapse processes, and where acts in the scales of the flux stop. In a case where this flux stop is affected by downflows. So basically the magnetic flux stop is having flows that's going downwards, making that the imbalance of the horizontal pressure inside of the tube that is balanced again due to the compression of the tube and increase of the magnetic field. The final one, this is the one interesting in this work, is true vortical changes. This was just only studied in simulation and was not observed in the sun. It's basically due to in regions of high vortical like flows, of plasma flows, there is like an interchange between the energy of the vortex that also is transferred to the magnetic field. So there's an increase of the magnetic field. So here I report the observational evidence of this sequential intensification process in a one magnetic bright point that is affected by convective collapse and vorticity changes because it's localized in a so-called intergranular vortex flow. The data set that we find this event, it's really special because it's a really well quality data set detected, recorded, by the Swedish Solar Telescope. They have a lot of information, several multi-wavelength information. We have lines of full polarimetry of the iron line, the photosphere, the 6173 nanometers. We have the calcium and the infrared, 8542 nanometers, and we have full spectroscopy of the calcium 2K and the H alpha. We did a lot of analysis in this data set. We initially detect the magnetic bright point with the information of the magnetograms retrieved by the Millet into called BFIST. And then we track these magnetic bright points with JAFTA code. And in this region that you see marked with the square, in these tiny regions, more or less far from the network regions, we identified this event. We did an analysis of the horizontal velocity pattern. We inferred the velocity pattern in the surface using DeepBulb, a machine learning tool that retrieved the information of the horizontal flow based on the continuum images. We perform Stokes inversions dependent in height with the SIR code, the sector analysis of the lines, weak field approximation of the lines, characterize the calcium 2K spectra, and also we try to make some classification of profiles. So I'm going to show you the result. So this is a time series, as you can see in the right, time series of two quantities specifically, the magnetic strength and the line of sight velocity. You are seeing two plots, one above and one below, that corresponds to two different spatial scales that we consider in the magnetic bright point. In the left side, you saw 4 maps, which are like a snapshot of mark for this arrow at the moment at 0.9 minute. This event lasts more or less 8 minutes. And you can see in the upper part, left side, the areas that we consider that we hold are like the full magnetic bright point and the core magnetic bright point. So you can see the evolution of these parameters in time. Here I want to just show you the first stage of the convective collapse processes. So you can see that most of the magnetic bright point is characterized by that downflow. So in the lower part, you can see, I want to point out this, sorry, sorry for the people online. So I want to point out that this like maximum values of downflow velocity more or less around 1 kilometers per second. And then before in the core, you can see like the maximum value above this kilogauss field. So this makes us think that we are starting to see the process of convective collapse. You can see here the line of sight velocity marked by red and blue, and the distribution of the magnetic field, like the longitudinal magnetic field, and something that we, and a quantity that we defined as a net circular polarization would give us idea of the gradients in velocity in height. So if we continue in time, we detect initially the signatures, the signatures of the vortex flow. So the pattern of the horizontal velocity that we identified, it's making an abortical movement around the magnetic bright point or in the area of the magnetic bright point. You're still seeing the downflow. So you're seeing the maximum downflow in this case, and the diminishing of the intensity, at least in the region of the core that we define at the core. If we continue advance, now the vortex flow is localized in the middle of the structure. Then we have an effect that comes after for the convective collapse, which is like was described by Belot Rubio here present. It's the rebound shock that you have like a flow that is going up in the center of the structure that usually is able to destroy the magnetic structure. In this case, you're seeing that the net circular polarization, which is the down plot with color green, shows extreme gradients in velocity because there's a like huge asymmetry of the Stokes-B lines. You expect for this case that the vortex, the magnetic flux structure is get destroyed because of the emergence of this flow upwards. But instead of that, what happened is that it get more intensified. In this point, the vortex flow is observed, but after a minute is no longer observed, and the magnetic bright point gets an intense deformation during that time. Now the flow in this period of time between 3 minutes is most going up flow. So this is the important part that I'm going to talk about in a second of the case of the chromospheric effect. At the end of the life of these magnetic bright points, possibly there was another convective collapse attempt, but it doesn't happen to keep the structure like alive. So I want to just briefly mention the chromospheric counterparts. So if you saw an image of the H alpha line at different position, you can see the clear structure of the chromospheric swirl that this is rotating around, and which is more or less like reminds us this idea of the solar tornado. So I'm going to show briefly the 3 effects that we saw. We try to explain what we are observing with a little draw. We are seeing that chromospheric drain at the beginning of the sequence. So it's following the idea of the convective collapse. So it's draining off the plasma down. Then there is like an effect of this upflow going, the effect of the rebound shock. We are seeing like shock waves going above. And this is characterized by the observation of chromospheric grain, which is the signature of an acoustic wave that steps into the shock in the middle of chromosphere. Finally, we saw that the dissipation of the shock of specific height clearly exposed the vertical structure of this chromospheric swirl, showing also the release of a bunch of material going above, and the exhibit that they on a jet in a minute. So we are seeing like in a specific jet on a rapid blue shift excursion of a spicule that is related to the release of this event. So I'm going to finish now. This is my last. So on a conclusion, we have like now observational evidence that this amplification of magnetic field based on different process of asynchronous process of convective collapse as initial amplification, and then that a prolonged magnetic field amplification due to changes in local vorticity. We saw the formation of the rebound flow going upwards that makes the connectivity between the photosphere and the chromosphere. And finally, we were able to observe that there is like a specific effect in the chromosphere based on the atmospheric vortex flow that is associated with this evolution of the magnetic field inside of the magnetic bright point. Just like to if you are more interested to this work and to give a look at all the analysis in the chromospheric part, which I missed some of them, please give a look at the following paper that's probably going to be published soon. So thank you so much.
Questions? This is not working. Okay, now it's working.
Great. Thank you very much for presentation. Actually, we published several papers on modeling such vertical motions, and in particular, we see very similar effect what you notice in observations. And I want just to mention, I don't know if you have enough spatial resolution, but actually you have to see upflows on periphery of such vortex tube and strong downflows just in vortex core. Sometimes it is visible, sometimes not. It kind of depends from dynamics of this vortex. Thank you.
Just a comment, we are seeing that extended structure that it makes an downflow that is draining, rounding the structure, and in the middle, because, well, this is the problem more or less of the formation of the line in this case, because if you're trying to see more in the center of the structure, you're seeing more deeper, so probably there is not so much movement, like at least vertical movement in that. So I'm not resolving, I think that I'm not resolving the real velocities at this as really the center, but I'm seeing that the flow is rotating around it with different senses. Sometimes it's going down, sometimes it's going up. So it's like a complete surreal structure.
Hi, Amy Norton here. I have a question. I know you have fantastic data.
Yes.
I'm wondering, what's the difference in signatures between convective collapse and small scale magnetic reconnection if you only have, if you have Hinode data or HMI data? Is there a very easy way to determine the difference?
I think that this is not easy way to determine it. I'm just only assuming that my at least in this case, and just in this magnetic bright point, there is at least no visual evidence of the reconnection, because I'm only resolving positive, one polarity, sorry, yes, one polarity. So there is a probability that happen at scales of kilometers or even meters for sure. But in this case, I'm assuming that this flux stop is just only one polarity and is getting amplified just by the fact that there is is localized in a downflow region.
Thank you again. So there are a few more questions, but we have to go to the poster presentation. So please ask during this time also. Poster time. You want to connect? Me too. I can connect you. Are you sure? Yeah, connect here. I do have it. So this is the last session of the focus meeting number 8. Thank you very much, everybody. So let's start with Jean-Pierre Roselot. So
when is it?
This is for going forward and back.
Forward and back. Yes. Okay. First of all, thank you, Sasha Trosovichev, for organizing this very nice meeting. And my talk will be maybe a little bit descriptive, but my goal is also to give some work to young people and theoreticians too. Well, the solar rotation is a very complex mechanism, as you can see here. There are two layers. One shear layers. One is a Tatter-Klein, which is very well known, which is a seat of the differential rotation. And there is another shear layer near the surface, very near the surface. And I shall speak about this very near subsurface shear layer. And also another thin layer inside this one, which we call the leptocline. Some key points to my mind to understand better the solar rotation. One is how we can couple large-scale flows, which are crucial for maintaining the sun's global magnetic field. What is the role of subsurface magnetic fields? The role of granules and supergranulation. We do not speak too much about that in this meeting, but I think it is important. The influence of magnetic fields on acoustic waves, excitation, propagation, and also maybe the torsional oscillations, as Sasha Trosovichev mentioned yesterday, to understand the solar cycle. And well, the growth of supercomputation enables better simulations. Well, about 20 years ago with Jeff Kuhn, we measured the solar limb variation with with the help of MDI. And we did that with the expansion of the gravitational potential. And the shape of the solar shape can be found with coefficient, which are called shape coefficient, H2, S4, and so on. And we were able to determine fairly well the taut line, and we were happy with that. And we did not notice too much at that time the bump which was near the surface, and that we called the leptocline. By analogy to the taut line in Greek, tachos is speed, and leptos in Greek is sin. So we thought that there was here a very thin layer, and it is the first time that this subsurface layer was evidenced by other means than heliosismology. From MDI or even HME, the conventional heliosismology conversions lead to a resolution of what is called the seismic solar radius. So the inversion of relative frequency variations which is the relative frequency variation, which is at left. And so we inverse this equation without forgetting a surface term, which takes into account the surface magnetic features. So by inverting this, we obtain what is called the fundamental seismic radius, which, and you can see here that the change of the seismic radius occurs mainly in a thin layer, which is about at -5 million millimeter or 0.992 fractional radius. So there is an expansion and the contraction of this with time of the flow, and we may estimate the variation of this fundamental radius by about 2 kilometers, but it is not very important. This is maybe not very important. What is important is that the variation with time and depth is just beneath below the surface, but about 5 million meters. It is known that the F radius, the seismic F radius value, is lower than the conventional adopted, the photospheric one. And in order to have the corresponding between the F radius and the photospheric one, you can imagine to extrapolate L to infinity, but Goose recently shows that it was not possible, because if you do that by mathematical, by mathematics, you have a photospheric surface, which is like a phantom. So it's not possible, and another possibility is to go to the P modes, and we can define here not the fundamental radius, seismic fundamental radius, but an acoustic radius. And the main interest when doing that is that this acoustic radius probe non-homologous layers inside the sun. This was done here when on this inversion equation, when you take the fractional change, each in the radius is not uniform, what happens? And what happens as results, you can see that there is something which which appears very well. It's at the fractional radius at 0.99. There is a kind of inversion point, a saddle point, as we can see. There's something like two regimes, one before and after that, and after and another after this point. So you have here about you can see here this very thin layer from 0.975 to near the surface. Obviously, we can cut at any fractional radius, and we can extrapolate to the surface. And if you extrapolate your surface, you find again radius variation of about 2 kilometers with time. But it is important to keep in mind that without high L, we cannot constrain the surface radius better. Now, the second parameter which we can use is the average radial gradient, which is shown here. The average gradient is about -1. At this saddle point, this point as I showed you before at 0.99 fractional radius. So this is mean average gradient, but it is lower below, and it is steeper above, and very steeper up to about -3 at 1.5 million meters in depth, the depth that I showed you before. And also this radial gradient of solar radiation rays varies with the solar cycle. It is more or less more negative than the average, while in quiet regions, the radiance is less negative at this depth. And close to the surface, this relationship appears to be reversed, as well as in latitude. At a latitude of about 50 degrees, this gradient of solar radiation change. So this is taken from Tom, and you can see in the upper left the variation of the radial gradient, which passes through about -0.4 to 0, and it's very strong below. And you have on the right the evolution with time, and we can see also that there is a strong variation of this radial gradient of solar rotation. Simulation has been, some simulation has been made by Irina Titashvili 2 years ago, and the model used is written there as about bots of about 80 million meters, and the vertical domain, which is about 25 million meters. So this model permits to give a significant decrease in the azimuthal velocity at 30 degrees of latitude, but you can see that there is a very deep, very steep change of this rotational rate. So they identify near surface shear layer is what we call the leptoplane again. So my conclusion will be like that. What is important is maybe there is likely two regimes. One is the dominant process in the boundaries and could be different from those in the main body of the shallow layer. And maybe in this shallow layer, the solar cycle can take some rules. Thank you.
Thank you very much. So we have time for questions.
Jean-Pierre, thanks for the interesting talk. So what defines the depth of the elliptic line? What physical process? Why it's 8 megameters deep, or is it depth of supergranulation, or what?
I don't know exactly what is the physical conditions inside this layer. So we observe this layer. It's confirmed by simulation made by Irina. But what is exactly the physical conditions in these layers? So I do not know it for the time being. It was, I said, word for young people. Maybe.
I have one question also, because one figure you presented kind of shows that the depth changes with the solar cycle. Is that so?
Yes. Yes.
So it's
Yes.
it responds to the magnetic field.
It corresponds to the magnetic field.
Okay.
That's right.
Thank you. And my question is about your measurements of solar radius, and how difficult is extend data what you presented. I mean, variations of solar radius with time,
Yes.
because it will be interesting to see how much solar radius vary from one cycle to another.
This is the time on for analyzing the data. So you have the time here is 2 solar cycles, about 2 solar cycles, 24 and 20, and beginning of 25.
Another question here.
Your very last question. Can you show your last slide? It's your very last question was very interesting because
which one?
Yeah, the last slide. Very last kind of conclusions. So what? Yeah, the previous slide. Yeah. Here it says, does the solar cycle take roots in the shallow subsurface? And recently was a paper published in Nature.
Yes.
That by British scientists. They claim that the whole solar cycle, it's not it's magnetic rotation stability in this layer or something that is, it's only the shallow layer. So what, can you comment on this?
I saw this paper, and there is also another paper which appeared about 1 week ago, and in the paper 1 week ago by Jane, they claim that the solar cycle takes roots in this shallow layer. I had no time to incorporate the results, but it is more or less it is more or less the same as this here. So.
Okay, so thank you again. So next talk is an online presentation by Alfio Bonanno. So you're ready, Alfio?
Hi, Gustavo. Let me share the screen. Okay, do you see my screen?
Yes, you can see. I will tell you when you have 5 minutes left, okay?
Okay, thank you very much. I would like to thank the organizers of this focus meeting, particularly Sasha Kosovicev, for the possibility of giving this talk. Unfortunately, for several reasons, I could not attend in person. So let's try to understand what is the solar dynamo in connection with the stellar dynamo or stellar activity cycle. So that's basically was already mentioned before. The let's say summary of several observations over the years using mostly, let's say, Mount-Wilson S-index to trace the activity cycle. And as you can see, there are a number of papers where they try to estimate whether there is a trend of rotational period with the cycle period, and the situation is rather confused. And so a few years ago, I decided to make a new catalog with about 70 well-detected stars with the periods, including the sun, and reanalyze all that in a completely new approach. And the approach, which is, I think, is the most rigorous, is the Bayesian one. So, so let's say that the kinematic dynamo theory will somehow imagine that omega cycle is proportional to the rotational rate with an index which can vary from 0 to 1 over half. I will go back to this point. And the key idea was not deciding by hand which type of slope we had to take in interpreting the data, but to use the Bayesian analysis, comparing, let's say, in the log-log plot, one single relation and two simultaneous relations, let's say two branches of type A and B, and ask whether there is a stronger Bayesian evidence for one case in the other case. So it's a much more complicated thing that you have to do, because you have to use now compare a much larger parameter space, which much more complicated likelihood, as you can see. But the answer was basically extremely clear. I mean, the two branches solution is the more, let's say, is statistically far more favorable than one single slope. So there are two branches. And these two branches, as you can see here, corresponds to stars. In the G1 case was frequencies of the cycle increase with the rotational frequency, and other G2, where the sun is, where the frequency of the cycle decreases with rotational frequencies, okay? And we try to understand what is the reason for that at the moment. And we had some hint that metallicity can play a role in this distinction, but I'll get back to this point later. So, if you have this dichotomy, we would like to understand which type of dynamo is in G1, which type of dynamo is in G2. So let's recall what is, let's say, the simplest, let's say, that result from mean field dynamo theory that you can obtain just solving the induction equation in prescribed Cartesian geometry, but in spherical geometry will not be much different for the dependence of omega cycle from the differential rotation. As you can see, the formula is that what you can see over there. And if we are in the pure alpha omega regime, where omega is very large, then this omega cycles goes to, let's say, a constant, which is k squared times eta. But on the other hand, if we believe mixing length theory and we express eta in terms of turbulent velocities, what we get is that if the dynamo is critical, the ratio between the cycle periods and the connected turnover time is more or less a constant. So constant means that should not depend on rotation, let's say, on the Rossby number. So is this the case in this case? Now we have to understand one important point of the discussion, that convective turnover time is not directly observable. So we have to get this quantity out of some prescription. And as you can see, there is a number of prescriptions already, how to get convective turnover time as a function of the excess of color It's very famous paper by Noyes, and then other paper by Wright and whatever. And but none one of those papers has really, let's say, a precise definition of tau in terms of the location of the convective turnover point inside the convective zone. We would like to have a definition of tau which is somehow, which tells us something about the dynamo, the stellar dynamo. So motivated by that, a few years ago with my collaborator Enrico Corsaro, we decided to use this definition. We know that average convective velocities can be described with very good approximation by this simple law. It's luminosity of the star times radius of the star over the mass of the star to the 1/3. Now, if we know the convection zone, we can define a convective turnover time, as you can see below. And surprisingly, this definition gives a rather good estimate of the local convective turnover time at the base of the convection zone, which you have to have a prescription to define this thing. Otherwise, if you go exactly at the bottom of the convection zone, this tau is infinite, it makes no sense. So this definition has the advantage of being, let's say, physically motivated, and also it gives a reasonable number for the convective turnover times for the sun, which is about 40 days at the base of the convection zone, which is a very different number that convective turnover time used by Noyes, which corresponds to 12 days, and it corresponds to something which is in the middle of the convection zone. It has no direct, connection with the dynamo mechanism, if we believe that the dynamo is sitting at the tachocline or something close to that. So what we did is to calibrate this tau using asteroseismology, using the legacy stars, for which we know precisely the excess of colors, and we did the Bayesian analysis for that, looking for various type of functional dependence in terms of BMV color excess, of Gaia color excess, and it turns out that a quadratic law does the best job. And that's what we recently published a few years ago. That's you can find the new calibrated tau legacy convection as a function of Gaia color and BMV color. And the comparison with the other tau in the literature is pretty good. If you can see this paper by Irving et al., which was published years ago, and only in the very deep region of M dwarf we have discrepancy, but our definition of tau works extremely well for main sequence G, K, and for S stars we have to be more careful, but for G, K, and some of the M stars, I would say it's pretty reasonable definition, which because we have now excess of colors, we can in principle use to explore the convective turnover time in a huge number of stars. So now we are improving the situation when including better measurements of the excess of color with Gaia, including the reddening, but that is a work which I'm at the moment currently on with Travis Metcalfe and other people. I won't say more about that, but now let's go back to our cycle period and see what happens if we measure cycle period as a function in units of tau and rotation in units of tau in group 1 and group 2. As you clearly see here, group 1 is basically constant. The distribution of group 1 in this log space is telling us that those stars have basically p cycle over tau, which is nearly constant. And we might interpret this as a prediction of mean field dynamo theory. We will say that those stars in group 1 are stars which are in the saturated regime, while stars in group 2, they do have, as in previous case, a negative slope. So what's the reason of the negative slope? Well, that's something which one can imagine is connected. Remember, it's the sun is in group 2 with the meridional circulation, because if we apply just angular momentum conservation along the toroidal direction, that you expect that the meridional flow should decrease as a function of omega. And therefore, because we know that the cycle is decided by the meridional circulation and the vector-dominated dynamo, you would expect that omega cycle is negative. So the question is, okay, we have an explanation for group 1, an explanation for group 2, and now the question is the solar dynamo supercritical or critical? No, okay, G1 is basically critical. What happens in G2? So that's something which a new approach, and I'm trying to present some new results for you in this occasion. And we try to understand, I'm trying to understand this looking at the monthly sunspot data. There has been a lot of papers prominent work in this direction, trying to discuss 1D with a 1D, let's say reduction model, the distribution of monthly sunspot data. And I'm just quoting a few words of prominent work on this direction, but I apologize if I'm missing some work on these things. So the idea is to use a fully different approach that has been from extremely, from what has been published so far, which use basically machine learning to explore, get the equations, the dynamical system out of the data. And in particular, I'm using a sparse identification of nonlinear dynamical system, which is a method to discover governing equation from data and get the parsimonious model that describes the underlying dynamics. How does that work? Suppose we have a dynamical system, a system which was states evolves over time according to a set of rules. You want to use a sparse regression, which is a very special type of regression, which is basically encode the physical requirement. We only would like to discuss physics when we have a small number of law that selects only a small number of significant terms. And then you have the library candidate function, set of possible functions that might describe the system dynamics, okay? Polynomials, trigonometric functions. So that's how it works for the Lorentz system. Suppose you simulate real data with a Lorentz system in this way, and you basically get this very long time series of simulated data. You construct a matrix once you have the data, which would like to basically solve this type to invert, let's say, the data and get back the coefficients. And to be more, let's say, to go back to the machine learning approach, the features here are the derivatives, okay? That the data at the derivative is computed for each time step from your time series. The theta of x is your matrix, and at C1, C2, C3 in this case of Lorentz system is your input vector. So the algorithm basically want to solve this huge sparse matrix. It's a very huge matrix because imagine how many data we have in the case of monthly sunspot numbers, and we train the algorithm on the data we have next to predict what is the outcome in X dot. Okay, and once you do that, that's the result. You basically get this nice dynamical system here, which even though we ask for a library of 6 let's say, polynomials degree 6, we always basically get the minimum with the library of at most cubic polynomial.
4 minutes, Alfio.
How many?
4.
Yeah, okay. Remember that x naught is b phi, x1 is derivative of b phi. And that is the answer. That is the, let's say, the global fit solution that we get to the Monti-Saspot number using this technique. And I would say this is an encouraging result. So far, I only saw in the literature fitting of dynamical system cycle by cycle. That's the first time I see a fit for the global solution. That's the phase-space reconstruction from that. The blue line are the data, and the orange line is what we reconstructed with that. And then now we can understand, we have dynamical system. We can do backward, say, reverse engineering and understand what is this dynamical system telling us. And it's telling us something interesting about the structure of the induction equation. For instance, because we have a y square x term, that will mean that in the quenching term, we don't only need a b square, but only would like to have to include the dt b phi square. Okay, and this very simple system can be analyzed with the dynamical system analysis, and it turns out that in our case, the sun is described by an unstable spiral, which means that the sun, I would interpret this the sun being supercritical, and nonlinearities get the sun back to the critical case. So this is a work in progress at the moment. So the conclusion are following that Rossby number is definitely a key quantity in interpreting stellar activity cycles, and would be nice to see numerical simulations results really discussed in terms of the Rossby number, and not in terms only and in terms of physical quantities. Okay, and we do find that active stars can be classified in 2 classes, as we've seen, and G1 group can be interpreted as a critical dynamo action, while in G2, like the sun, it's possible to interpret the dynamo in terms of a low-order dynamical system in a global way. I would say that's probably the first time I've seen something like that, and it is super critical, and we hope to present finally some prediction very soon. Thank you.
Thank you very much, Alfio. It's very interesting.
Thank you.
Questions, please? Irina.
Hi, Alfio. My question is about the estimation of overtuning time. And can you discuss a little bit about correlations between overtuning time and magnetic activity of stars?
Correlation is this plot. That is Rossby number, P cycle as a function measured in units of tau as a function of the Rossby number, which is the rotation as a function in units of, of the turnover convective time. So, and I see clearly that these 2 populations are still there.
I'm sorry, it is not magnetic activity.
Why not? This magnetic okay. Magnetic activity, we analyzed that at the beginning here. And here we have log 10 R prime. We perform Kolmogorov-Smirnov test on population 1 and population 2, and we did not find any possibility of discriminating between population 1 and population 2 in terms of stellar activity index. So this, let's say, usual discussion that we see in papers like this one, where we trace branches in terms of the activity cycles. And that was also in the paper by Lehtinen, I think. It's not there. It's not really possible to say that we have an active branch versus a non-active branch. That doesn't, statistically, that does not happen to be the case.
But what is the figure at the bottom right telling you then?
That is the figure at the bottom right, is log activity index for group 1 and group 2. And statistically, there is no difference from group 1 and group 2.
Really?
We did a Kolmogorov test, Smirnov test, and the p-value is about 0.2, 0.3. So to reject the null hypothesis, we need something like 0.03 at least, and that was only possible with the metallicity.
There is one online question, so Emre, please.
Right. Thank you, Alfio. Very interesting talk. My question regards this slide as well. So the question is, how pure are these stellar samples in terms of the convection zone depth, for instance, spectral type of the star? Because I would like to see, if we had enough stars, how a solar mass star, or how solar mass stars look at such a plot, or how just K0 stars or whatever. Well, but if there are several effects in it, then hard to interpret for me.
The stars are basically main sequence stars.
Of FJK stars, so very...
Yeah, there is some, there is a couple of sub-giant, I think, and maybe one giant, but mostly they are all main sequence statistics.
Okay, yeah. Then I think, I mean, my personal opinion is if you mix several masses together, like along the main sequence.
Yeah, that's true. But the spectral class, basically the evolutionary state is, in fact, we did not want to use, let's say, fast rotating stars or very strange outliers. We are more or less in the main sequence region, or slightly more, would say more evolved in some case. But
my second question is, how do you interpret that that additional term in the y-squared term? That was the time evolution of the toroidal field that you interpreted. I mean, what would its effect be in the induction? Sorry, in the solutions of the dynamo, let's say.
I mean, which term?
Yeah, that in the red expression, the lower right one, the TB phi.
Ah, the TB phi. That's a very good question. I think if you look at if you split the induction equation, toroidal part and toroidal part, the TB phi is proportional to the toroidal field.
Exactly, yeah.
So in a sense, this is telling us that all the magnetic energy has to be, I mean, that's the quenching.
Yeah.
And very, I will say, very natural thing to expect. And it's extremely interesting to see that from the dynamical system can be interpreted now in terms of mean field, let's say, plus nonlinear terms with quenching. I think that's to me, it's a very, very exciting thing.
Yeah, indeed, I think so. Thanks.
I have a question. So if you are interpreting this time series as a alpha omega dynamo, what happens if you consider an alpha square omega dynamo? You get the same solution?
No, I don't know. I get to check. So your question is if I use an alpha square dynamo, whether I get the same alpha square omega dynamo, if I would get the same or similar dynamical system, that I don't know. That's a very good point. That's a very good point, Gustavo.
This saturation mechanism is kind of suggesting that.
That's a very good point, and but this is really work in progress that I'm working here with Rainer at the moment, and we are discussing this thing. So I really wanted to share you to have feedback from you, but it could be possible that plays a role. Yes.
Okay, thank you very much, Alfio. Thanks.
Thank you for the possibility of speaking, for your question.
We have one more talk. It's Travis, please.
Well, thanks everyone for making it till the end. All right. In 2016, my close collaborator, Jennifer Van Saters, suggested weakened magnetic braking in old solar type stars as a way of explaining some observations of Kepler field stars. And I've spent most of the last 8 years really trying to understand what drives weakened magnetic braking in these stars and in new samples of similar stars. So what I'd like to do today is sort of give you an overview of the both direct and indirect evidence for weakened magnetic braking in old solar type stars. Then I'll discuss 4 key empirical clues for dynamo theorists about how and why this manifests that you should aim to reproduce with simulations. And if I have time at the end, I'll give you sort of a qualitative argument for how this sort of plays out in observations of the sun, for example, where we have a very close-up view. Okay, so the original evidence for weakened magnetic braking came from observations of old field stars with ages measured from astroseismology. And the basic observation was that old stars were spinning faster than you would expect if they continued to spin down over time, like the Skumanich relation, now 50 years old. And it did so in such a way that it deviated from standard spin down earlier in hotter stars and later in cooler stars. So the sort of F-type stars on the right, G-type stars in the middle, and K-type stars on the left, you can see standard spin down predictions is the sort of blue contours, and weakened magnetic braking postulated that at a fixed Rossby number, a single parameter, stars would begin to, basically magnetic braking would shut off, the simplest assumption that you can make. And this idea basically explains this indirect evidence of stalled spin down or weakened magnetic braking in old solar type stars. And this is the most recent work from Jennifer's graduate student, Nick Saunders, just published last year. And the best fit of that critical Rossby number where weakened magnetic braking begins is about 90% of the solar value. So suggesting that our own solar system is already in this weakened magnetic braking regime. Okay. So that's the indirect evidence. And what I've been trying to do is get more direct evidence of how this actually, what's causing this. So the direct evidence has to come from direct measurements of the large scale magnetic field. And the reason for that is the large scale magnetic field, think dipole field, carries most of the angular momentum from the magnetized stellar wind. And spectropolarimetry is the tool of choice to measure large-scale magnetic fields. And in fact, for distant stars where we don't have spatial resolution, it's only sensitive to the large-scale field. And so you can think of it as a binary test for the presence or absence of that large-scale field. So here we're looking at okay, so you have to combine spectropolarimetric measurements of the strength and topology of the magnetic field with some estimate of the mass loss rate, generally from a scaling law with the X-ray luminosity, the basic stellar properties like mass and radius, and the rotation period. When you combine those things, you can estimate for any star where you have all those quantities, the wind breaking torque, or equivalently the angular momentum loss rate, okay? So what we're looking at here is a sample of a dozen stars where we have all of those measurements assembled to be able to make these estimates over the past 5 years using the Large Binocular Telescope and a beautiful spectropolarimeter built by Klaus Strassmayer. And so you can see we're looking, the vertical axis is the wind breaking torque normalized to this star HT 76151 as a function of the Rossby number normalized by the solar value. And the standard spin down model is that a dotted yellow line there would predict this gradual decrease in the wind breaking torque over time. But in fact, what we find in the sample is that at a critical Rossby number, there's a sudden decrease of about an order of magnitude where you find all of these other sun-like stars, including the sun, in fact, and then it continues to decrease beyond there. Down Tau Ceti is more than 2 orders of magnitude weaker. So there's a clear break where weakened magnetic braking appears to kick in from these direct measurements, and empirically, the value of that critical Rossby number is about 90% of the solar value, just as we found from the indirect evidence from rotation. Okay. So that's the overview of the evidence for weakened magnetic braking. And now I'd like to sort of summarize what we think this tells us about stellar dynamos. Because after all, this is being driven by changes in the magnetic field. So, okay. So first, why should we expect slow rotation to weaken the large scale field? Well, if we look at the sun as an example, rotation and the Coriolis force and other Reynolds stresses really drives several things that all contribute to the regeneration of the large scale field. So the Coriolis force, as we saw in Hannah's talk yesterday, contributes to the tilt of bipolar magnetic regions as they emerge. The Coriolis force and other Reynolds stresses also naturally produce both the differential rotation and the meridional circulation. And so as you can imagine that there might be a critical rotation rate where the Coriolis forces are no longer imprinting a significant signature on the convective patterns. And so you're reducing the Joy's law tilt that prevents the differential rotation from separating the leading and trailing polarities over time. And so more of the flux cancels before meridional circulation, which is also weaker, can transport it to the pole and seed the generation of the large scale field. So it's a natural explanation for why we might expect for some critical rotation rate where the large scale field might begin to weaken, as is observed in these older solar type stars. The second clue that we noticed actually almost immediately was that if you look at, this is a plot that you've already seen in Alfio's presentation, the cycle period in years versus the rotation rate, you see that there are a couple of different correlations between those things. But if you look at this series of solar analogs, HD 76151, 18 SCO, alpha Cen A, and 16 Sig, it seems that stars spin down until a critical rotation rate, this critical Rossby number for that given spectral type. But then cycles appear to grow longer and weaker until in 16 Sig, this is a flat activity star. It doesn't have cycles. And so what it seems is that at that critical Rossby number, at that same critical Rossby number where weakened magnetic braking kicks in, cycles are getting longer and weaker over the second half of the main sequence lifetime. And this same pattern appears in both hotter and cooler stars. And that was what allowed us to select our initial sample, looking at these stars that have similar rotation periods, but very different activity levels and cycles or no cycles to try to pin down this behavior. And note that the solar cycle, being in the middle of these two different branches, is a natural feature of our theory, because under this understanding, the sun is already beyond the transition and it is moving upward. The solar cycle is getting longer and we might expect it to disappear sometime in the next couple of billion years. Okay, this is kind of reinforced if you look. The critical Rossby numbers, since activity level and Rossby number are correlated, you can kind of translate the critical Rossby number into a critical activity level for any given star. And if you look at a star with a well-defined cycle like Sigma Draconis that's below that critical value, it shows nice, well-ordered cycles where the minimum corresponds roughly to that critical activity level. But as stars age and their average activity level decreases over time, you get a case like HD 16620, which is the only, the first confirmed Maunder minimum star where it had cycles during the Mount Wilson survey, but then since then has shown 20 years of constant activity. So it's gone into hibernation. And its critical activity level is there at about its average activity level. So it's evolving. You might expect that as stars evolve through this critical activity level, the cycles can become intermittent, and you see these effects like grand minima. But then eventually, evolving towards subgiant phase like 31 Aquila, the average activity level eventually gets so far below that critical level that even the most extreme active regions that are like anti-joy or anti-Hale cannot kick it, the dynamo between the cycling and non-cycling phases. So it's too far below for even the most extreme events to do that. And you go into a permanently flat activity phase that we see in a lot of these old solar type stars in the Mount Wilson survey. The last clue is super exciting because it's a really direct test of this idea. In 2020, we found this star 94 Aquarius AA. It's a subgiant with a very clear cycle. And when we tried to model the rotational evolution, we found that it was in this very special evolutionary state just before ascending the red giant branch. So the idea here is that, that 94 Aquarius A, had a cycle probably when it was evolving in the first couple of billion years, but it hit the critical Rossby number. It parked at that critical Rossby number until physical expansion pushed it over the critical Rossby number and made the cycle disappear. But then later in the subgiant phase, it has a structural rebalancing where the envelope expands and the core contracts. You get the deeper convection zone basically overwhelms the longer rotation period from the physical expansion to increase the convective turnover time, so you can actually dip back below that critical Rossby number once again, briefly before ascending the red giant branch. And lo and behold, we find it there, and it now has a cycle again, right? So you can think of the onset of weakened magnetic braking at this critical Rossby number. That's the same critical Rossby number that defines where there are clear activity cycles below and flat activity stars above. Okay, so those are the 4 clues that I would like to see more people try to reproduce with dynamo simulations. These are great constraints for models. Okay, how much time do I have? Okay, so I have time to do one of this. So I mentioned how slow rotation might gradually decrease the strength of the large scale field. It also affects the other side of the dynamo loop, which is flux emergence. So if you have a large scale field, differential rotation will wrap it up and create buoyant magnetic loops at the base of the convection zone that emerge as new flux. Well, if the large scale field is weaker and the differential rotation is weaker, you might expect less flux to emerge. And so it's a downward spiral. You've got a weaker large scale magnetic field. It creates weaker flux emergence. You have less flux to create more large scale field, and it just is a downward spiral. So there's a secondary effect that we've seen evidence for in our spectropolarimetry, that it's not just the change in the morphology of the magnetic field. There are secondary effects on the mass loss rate. And we can understand that as also like a side effect of the topology change that we see play out in our own solar system over the course of the solar cycle. Because mass loss goes along open magnetic field lines, and the amount of open magnetic field lines changes over the course of the solar cycle and on stellar evolutionary timescales as well. And so basically more complex field throttles the stellar wind. And so you can basically reduce the mass loss rate beyond what is expected in traditional models to further decrease the angular momentum loss rate, okay? So it's both a change in magnetic morphology and a change, induced change in the mass loss rate that is causing the weakened magnetic braking. Okay, and with that, I will put up my summary of conclusions. These are the 4 clues that dynamo modelers should try to reproduce with simulations if they want to reproduce this kind of behavior that we're seeing in old solar type stars. Thank you very much.
Thank you, Travis. Questions? There's one there.
So Travis, love this stuff, you know. So would the young sun have had a greater or lesser mass loss rate, given the scaling relation you just noted?
The young sun would have a much greater mass loss rate, yeah.
Good.
Although a very young sun also has a complex magnetic field, right? And so there will be some throttling in the early times, and this is what creates the persistent fast rotating sequence in young clusters, for example, right?
Thanks, Travis. So you now clearly have no problem in slowing down or breaking stars. What are the observational constraints that would be able to tell sort of the proportion which is due to the mass loss, which is due to the cycle changes?
We can actually estimate that, and we have in each of our papers over the last 5 years, just from the models, you can attribute, just by comparing different stars at different evolutionary states, you can just change one parameter at a time between those models to try to attribute how much is due to the mass loss rate change, how much is due to the topology change. And so early on, this is like 50-50, like about half mass loss rate changes that are beyond what's expected and about half from topology changes that were previously unexpected. Later, it gets dominated by the morphology changes.
Hey, Travis, so there are 2 other very independent observations from the sun as a star context, which really adds up to this and complements this. One is this observation by the Max Planck group, which shows that the sun is comparably much more inactive compared to stars which are of similar age to the sun. The other is a work by Ilya Ususkin, who shows that if we look at the long-term solar cycle activity, that is kind of oscillates between 2 phases, inactive monominima-like phase and a regular activity phase. And if you put that together with your observations, all of this suggests that the solar dynamo right now at this point in time is perhaps in a subcritical regime, where it is transitioning between an active phase to inactive phase, but right now has access to both of these phases. And we wrote a paper in 2021, I think in MLRAS, explaining how this can happen if you change the Rossby number and add noise to the system. And that sort of beautifully explains all these different observations nicely. So perhaps you could have a look at the paper.
Yeah, I'm definitely familiar with that paper. It is one of our inspirations for kind of bringing all of these clues together and putting it all together into this picture. One thing I'll say about the Max Planck result about the sun being unusually inactive for its age, if you control carefully for metallicity and temperature in that sample, that turns out not to be the case. I think subsequent studies have shown that the sun is perfectly normal for other stars in its same situation. Those other stars are also in the weakened magnetic braking regime, probably, right? So I don't think that is a signature of the subcritical dynamo. But the other part, I definitely agree. Yeah.
I have a question and one comment, Travis. So my comment is there are 3D numerical simulations since 2020 or something like this from different groups, and all of them kind of show that when the star rotates very slow, the dynamo changes from cycling to steady. This will fit your theory. And the second, or my comment is, have you calibrated your Rossby number with metallicity like, for example, Alfio did, because this could change the results or not?
Yeah, absolutely. As Alfio mentioned, we've been working together to try to improve the astroseismic calibration of the stellar Rossby number in a sample that is diverse in metallicity, temperature, surface gravity, all those things that might also matter. So that's an effort that's just beginning, and but is definitely important.
Travis, I have two questions. Thanks for the talk, interesting results. And first, not very clear why you relate mass loss with X-ray activity, because X-ray comes from closed loops, not open magnetic field. So it should be opposite relation.
Yeah, so the reason for that is, so it's based on Brian Wood's work, where there are, for a few dozen stars, direct measurements of the mass loss rate, well, let's say direct modeling of the inferences of the mass loss rate from Lyman alpha observations, and you get asymmetries where you can actually model the mass loss rate from very nearby stars. And in that sample, there's an empirical correlation between the mass loss rate and the X-ray flux per unit surface area. There is a lot of scatter around that relation, and that's another area where there could definitely be improvement. Yeah, but direct mass loss rates are possible for nearby stars, and we're working on that as well.
And my second question is that if you look at the sun, solar rotation, then solar core rotates uniformly, and differential rotation only in the convective envelope, and dynamo works only in convective envelope. So it seems that magnetic braking should be related to some primordial magnetic field that involves the radiative interior, not just to dynamo.
Yeah, possibly. I think that in the solar case, like, it's very clear that the sun still has differential rotation, still has a lot of the ingredients that we expect to drive a dynamo. The question is, like, how does the present state of the sun compare to how the sun was just 1 billion years ago? The sun was probably not in the weakened magnetic braking regime. And the issue is that the wind braking torque of that earlier sun is predicted to be about 10 times stronger than it is at the present day. So yeah, that's an interesting question. Yeah.
There is one online question, so Emre.
Yeah, I have just a comment on Dibiando's question and remark and Travis's reaction to that about the Max Planck results. I was not in that study, but I was, yeah. So, that those super active solar analogs, even though some of them have very similar metallicities, the thing is that they form only a subsample of the entire sample, and because they are periodic stars, so to say, in the sample, the non-periodics are a bulk of the distribution. So the majority of the stars in the sample are non-periodic, and the sun is also non-periodic. So one has to compare the sun with with these non-periodics as well. And when one does so, then these super active, like high variability solar-like stars are maybe outliers. That's also a possibility. That's what I want to say. And the question why is, yeah, maybe different patterns of magnetic flux emergence or whatever. This is still a riddle. Yeah. Thanks.
More questions? Okay, so thanks, Travis, again. Sasha.
So we have some time for discussion. And first, Dr. Han wanted to present his poster. Is Dr. Han here? Okay, so now it's time for open discussion. So please, if you like to discuss some problems or suggestions, that microphone is open. So maybe people online that what we don't know if I'd like to ask Günther Rüdiger if he's still online. Not? Oh. Okay, if people online want to discuss something, present. Nobody. Somebody in the room? Okay, no, then, okay.
I was just thinking about for my knowledge as I'm like an adjunct research currently. I'm curious about this, how people, I mean, researchers, you, and in particular people that make simulations, works with this that was presented about the convective conundrum. So there is any idea of what, I mean, this is wrong? I mean, this Mixed-Learning theory, this is wrong? Or this is right? I mean, this is just for my personal knowledge. I know whether this is any.
Gustavo is the best person to answer.
Yeah, I don't know. So I wanted to ask Alfio because Alfio, but Alfio is Alfio, yeah, Alfio. So Alfio, you showed that the Rossby number for the convective turnover time of the sun is kind of 3 times larger than the predictions or the early estimations. So this will mean that the velocity of the convective velocity at the deep interior is smaller, right?
No, sorry, Gustavo, it all depends how you define the convective turnover times. It's clearly, it's by definition, it is infinite at the bottom of the convective zone, no? Therefore, it's, and it changes with because the convective velocity are 0 at the bottom, and then it changes with the convective velocity. So 12 days is about the middle of the convective zone. Does that mean, do we want the Rossby number to trace the dynamo? The answer is, if we believe that the dynamo and the sun is distributed, then it's okay. Then it's a very good measurement of many a good quantity to consider. But and that was the reason why I think Noyes in the 80s had this idea. But if we now think that dynamo is produced by the tachocline, then we should have something which measure the convective turnover time near the bottom of the convection zone, but cannot be exactly at the bottom. Let's say few, let's say grid points in terms of solar modeling of the bottom, and something which makes sense is this number. So the question for me is whether you can extract the convective turnover time of this type from your numerical simulation, and you can really produce a cycle time over convective turnover time plot, dependency as a function of the Rossby number. But the question is, how do you extract the Rossby number from numerical simulation, and do we agree on that? I mean, that's the crucial point, because it's clear that if we look at mixed-length theory, everything is simple, no? And there is no dependence of rotation already in the convective turnover time. Now we have to do, for interpreting the numerical simulation, this is not obvious to me.
Okay, thank you. I can comment from observational point of view because I know how it appears. So we should blame Hilly seismology for this, because two of my colleagues, Tom Duval and Shravan Hanasogi, they did measurements of convective velocities. What they did, they used a simulation model from Mark Mish. Mark, no, he's online, yeah. And then they calculated travel times, acoustic travel times for the model. This way, they calibrated measurements of travel times on the sun. And they found that convective velocity is much smaller than predicted by the model. So now the question is how accurately they calibrated this. So then the whole story started from these measurements of Hilly seismology. It was not very deep. It's depth like maybe 20 megameters, but convective velocity is much smaller. So then people start thinking about what to do about this. This conundrum appeared and all this. So what we are trying to reproduce this using Gustavo simulations with high resolution and some better calibrated local heliosysmology. So I had two students. Unfortunately, one of them left the field for business, and so what now we're still trying to still working on this problem. So but the key issue is to improve heliosysmology measurements. And
I have actually a question related to this. How surface effects affect on such problem?
Well, this is again, this is kind of what all using simulations to calibrate measurements, because doing actually it's student develop really a bright technique, deep focusing, and actually he was able to reproduce Gustavo's flow field at some depth pretty accurately. So now we're looking at spectrum of solar convection, and but definitely that the key here is why computation is difficult, because these models that Gustavo uses and the previous model, Mark Misch, they're unelastic simulations. These simulations don't model surface convection, which is critical. As this elliptic line appears, this fast downdrafts, it's all these. And the other type simulations that what Irina is doing and Matthias, that's only shallow layer, so they don't go very deep. So kind of, merging, because it takes a lot of computing time. So that's what Matthias wants to comment.
Few more comments. I mean, the entire story started with helioseismic measurements, but there are also, the surface flow measurement from David Hathaway, which also shows that the flow velocity at L equal 10, it's something like 10 meters per second. And if you look at surface simulations and you make the box bigger and bigger, you roughly agree with these flows up to a scale of supergranulation, but after that, simulations derail. So there seems to be some breaking point. What is really special about supergranulation is mostly that there is less power on larger scales. That makes supergranulation stand out. So, all these simulations, even though they're not mixing length models, they behave like mixing lengths, and that's mostly stratification. Mass has to turn over, and that leads to mixing length-like behavior. But there's something on the larger scales where the system seems to behave a little bit different. And at least in some simulation, it has been found that if you add a lot of small-scale magnetic field, you actually brings the convective power down on large scales, which points at least halfway in that direction.
It is very small comment, relevant what Matthias said. Actually, what we found in terms of scale increase with depth, actually it is only partially true, at least what I see. And actually, turbulent structures start change as you go below helium hydrogen ionization zone. So flows start look quite different.
Okay, and more questions, comments? So I'd like to thank everybody for participating in this meeting. And one last point, it was really very, very interesting, very important. And the last point that IAU wants us to publish some papers within 50 pages limit. And they don't want individual abstracts. We can put 50 abstracts there. They don't want it. So if somebody wants to present some parts of the meeting, please contact me. Okay, so it's a great opportunity. So this is proceedings of IAU proceedings, but they're counted as refereed by Scopus, and so it's only referred very lightly. So it's a great opportunity to publish some new ideas, even controversial ideas. So it's so if somebody wants to write, then please contact me. So I think Jean-Pierre already wrote something, and we can include in this. So please consider this. Oh, kind of overview of what we need somehow to present in IAU publications some outcome of this meeting. probably like 6 months, 6 months. They're not fast. Okay, it's more questions, comments. Okay, so then thanks everybody.